What if I told you that approximately 95% of our universe remains an enigma, a vast unknown that continues to elude our understanding? Despite having mapped countless galaxies and observed awe-inspiring cosmic events, a staggering portion of both matter and energy remains unseen. This invisible realm not only challenges our understanding, but also leaves many profound questions unanswered. From the explosive birth of the universe to the hidden forces propelling its ongoing expansion, we have only uncovered a small fragment of the vast cosmic tapestry. Join us as we embark on a journey to unravel these mysteries, pushing the very limits of science. Together, we'll delve deep into the hidden layers of the cosmos, sparking curiosity and wonder about the untold discoveries that await. The origin of our universe stands as one of the most perplexing and profound mysteries in modern science, with numerous theories vying to explain how everything we know came into being. The most widely accepted explanation is the Big Bang Theory. According to this theory, around 8 billion years ago, the universe emerged from an infinitesimally small, incredibly hot and dense singularity. In an instant, this singularity exploded, expanding at an unimaginable rate. Space, time, and all matter began to take form, ultimately evolving into the stars, galaxies, and planets we observe today. Yet, for all its grandeur, the Big Bang Theory raises as many questions as it answers. For one, what triggered the initial singularity to expand in the first place? While the theory thoroughly describes the evolution of the universe following the expansion, it offers little insight into the conditions that existed before that monumental event. Furthermore, the theory struggles to explain some observed phenomena. For example, the cosmic microwave background radiation is strikingly uniform, and the distribution of galaxies across the universe is puzzling. These unsolved mysteries have prompted some scientists to seek alternative models to explain the origins of the universe. One of these alternative models is cosmic inflation. This theory proposes that immediately after the Big Bang, the universe expanded exponentially in a brief yet incredibly rapid period. Another intriguing theory suggests the possibility of a multiverse, a reality where our universe is just one of potentially infinite others, each with its own distinct laws of physics and initial conditions. These hypotheses challenge the very notion of a singular, unique universe and open up new, exciting avenues for exploration. Another vast and largely mysterious domain of modern cosmology revolves around dark matter and dark energy, which together account for about 95% of the universe's mass and energy. Dark matter is thought to explain irregularities in the rotation of galaxies, while dark energy is responsible for the accelerated expansion of the universe. Despite their overwhelming influence on the cosmos, both remain poorly understood. Scientists are tirelessly working to uncover the true nature of these elusive components, believing that doing so could unlock even greater secrets about the origins and future of the universe. As technology continues to advance, the tools at our disposal, ranging from powerful telescopes to cutting-edge particle physics experiments, are providing new insights into the cosmos. Each new discovery brings us closer to understanding the universe's beginnings, yet the core questions of what happened before the Big Bang and the nature of dark matter and dark energy remain tantalizingly out of reach. These unanswered questions are not just academic. They highlight the immense frontier of knowledge that still awaits exploration. The more we learn, the more we realize how much remains to be discovered. To truly grasp the origin of the universe, we must first confront the complex, interwoven concepts of time and space. Traditionally, we have understood space as the three-dimensional expanse in which we live, where objects are placed, events unfold, and matter interacts. Time, on the other hand, has been seen as the relentless progression from the past through the present and into the future. However, in the context of the universe's birth, these familiar concepts take on a radically different meaning. According to the Big Bang Theory, the universe began as a singularity, an incredibly hot, dense point, approximately 13.8 billion years ago. At this pivotal moment, not only did matter and energy come into existence, but so did time and space. This raises a mind-boggling implication. Before the Big Bang, not only were there no stars or galaxies, but the very concept of before may not even have existed. Time, as we understand it, did not exist. This revelation challenges the very fabric of our intuition and forces us to reconsider the nature of reality itself. This insight pushes us to rethink time and space as inseparable entities, as parts of a four-dimensional fabric known as space-time. Just as matter and energy are bound by the laws of physics, time and space are intertwined, each influencing the other in a delicate cosmic dance. As the universe began its rapid expansion following the Big Bang, space itself stretched and cooled. This allowed for the formation of fundamental particles, which eventually coalesced into the first atoms, stars, and galaxies. In this new perspective, time is not simply a passive backdrop against which events unfold. It is an active participant in the ongoing evolution of the cosmos. The birth of stars, the formation of galaxies, and the emergence of life on Earth are all anchored in this shared timeline. Time and space are not static. They are dynamic, continually shaped by the forces of gravity and the mysterious expansion driven by dark energy. As the universe continues to evolve, so too do our understanding of these fundamental concepts. In this intricate and ever-changing interplay, the very nature of existence itself is defined. From the creation of elementary particles to the formation of the vast cosmic structures we see today, the universe is a story unfolding across time and space. The more we uncover, the more we realize that we are just at the beginning of a long journey of discovery. Every breakthrough, every new observation brings us closer to understanding our place in the universe and the cosmos itself. And yet, with every answer we find, we are reminded of the vast mysteries that remain. The relationship between the forces and principles governing our universe provides the fundamental framework of cosmology, offering us the tools to explore the mysteries of existence, from the very beginning to the ongoing evolution of everything around us. At the heart of this exploration lies the Big Bang, the pivotal event that marks the inception of our universe. Yet, despite our substantial progress in understanding the universe's development since that moment, the precise details of the Big Bang itself remain shrouded in uncertainty and mystery. The Big Bang is not merely a singular event, but the starting point of both time and space. 8 billion years ago, an unfathomable release of energy set in motion the formation of the cosmos as we know it. However, the moment itself and the exact process through which it unfolded continue to elude our comprehension. While we have a wealth of evidence detailing the universe's expansion and evolution following the Big Bang, the conditions at the very instant of its occurrence are far more elusive. One of the primary reasons for this enigma lies in the inherent limitations of our current scientific frameworks. Two of the most powerful tools we have at our disposal, general relativity and quantum mechanics, excel in their ability to describe distinct aspects of the universe, but they fail to unify under a single cohesive theory at the universe's beginning. General relativity governs the large-scale structure of space-time, while quantum mechanics accurately describes the behavior of subatomic particles. Yet, when we try to apply these theories to the earliest moments of the universe, a clear picture fails to emerge. Both gravitational forces and quantum effects were at play during the Big Bang, but our current theories are unable to merge these two realms into a single unified theory that can describe the birth of the universe. This gap in understanding leaves us with an incomplete picture of what happened in those first crucial moments after the Big Bang. To make matters even more challenging, the nature of the Big Bang event itself introduces an additional complication. The event marks a boundary beyond which our current physical laws begin to break down. This boundary is known as a singularity, a state in which our traditional laws of physics cease to function in any meaningful way. This renders the methods of scientific inquiry that we rely on, observations, experiments, and empirical data, less effective, as the very conditions at the Big Bang's core prevent direct observation. There are no experimental simulations or observations that we can reference to probe the universe's earliest moments. Instead, scientists must rely on indirect evidence and theoretical mathematics, piecing together a model of what might have occurred based on the available clues. Despite these profound challenges, the pursuit to understand the origins of the universe remains a central focus of scientific research. Astronomical observations such as the cosmic microwave background radiation, faint traces of heat left over from the Big Bang, and the distribution of galaxies across the cosmos offer important insights into the universe's early conditions. Further advances in particle physics, especially those aimed at developing a unified theory that reconciles quantum mechanics and gravity, offer hope that the puzzle of the Big Bang may one day be solved. Until that breakthrough comes, however, the true essence of the Big Bang will remain one of the greatest mysteries in cosmology, continuing to fascinate both scientists and enthusiasts alike. In the immediate aftermath of the Big Bang, the universe was an incredibly hostile and alien place. Conditions were far removed from anything we experience today. The cosmos was intensely hot, extremely dense, and composed of fundamental particles racing around at speeds that are almost impossible to imagine. Yet, recent investigations suggest that forces and phenomena we still barely understand may have had a critical role in shaping the landscape of this primordial cosmos. One of the most intriguing possibilities is the influence of quantum fluctuations in the first moments following the Big Bang. In the earliest fraction of a second after the universe began, the laws of quantum mechanics ruled the cosmos. These quantum fluctuations, tiny, random variations in the density of matter, could have seeded the formation of the large-scale structures we see today, such as galaxies and clusters of stars. As the universe expanded and cooled, these small initial variations could have been amplified, eventually giving rise to the complex structures that populate the cosmos. Understanding how such minute quantum events could have far-reaching, large-scale consequences is a key area of active research, sparking curiosity about the profound interconnectedness of the very small and the very large. Another potential force that could have shaped the early universe is dark energy, a mysterious form of energy that we know little about but is believed to be responsible for the accelerated expansion of the universe today. If dark energy had a more substantial role in the early universe, it could have influenced the rate at which different regions of space expanded. These early dynamics would have been crucial in determining how matter was distributed across the universe, and, ultimately, how galaxies, stars, and other cosmic structures formed. While our understanding of dark energy remains limited, its potential influence on the early universe makes it a critical factor in the ongoing search for answers about the cosmos's origins. At the same time, the force of gravity, governed by the mass of particles in the early universe, also played a key role in shaping the cosmos. Gravity pulled matter together, leading to the formation of the first structures in the universe. However, it's still a topic of heated debate among scientists whether gravity alone was sufficient to explain the behavior of the early universe. Could there have been other forces at work, potentially linked to undiscovered particles or realms of physics beyond our current models? This question remains open, and scientists are actively seeking evidence that might reveal new aspects of gravity or even new forces entirely that played a role in the universe's birth. As our understanding of the cosmos deepens, researchers are making progress toward uncovering these unknown forces and mechanisms. Understanding the forces that shape the universe's early moments could revolutionize our understanding not just of the beginning of time, but also of how the cosmos continues to evolve. In particular, the pursuit of knowledge about the first few moments after the Big Bang could lead to a richer understanding of cosmic evolution, providing us with a clearer picture of how the universe transitioned from a hot, dense state into the vast and complex system we observe today. Exploring the birth of the universe is no small task. It represents a journey into realms of existence that current physics cannot fully explain. Yet this very pursuit holds monumental implications for our broader understanding of reality. If we are able to unravel the mysteries of the Big Bang, we may gain insights into the fundamental laws and forces that govern everything we observe in the cosmos. For example, theoretical frameworks such as quantum gravity aim to bridge the gap between the known laws of physics and the extreme conditions present at the beginning of the universe. Should such efforts succeed, they could lead to a revolutionary understanding of gravity on a cosmic scale, reshaping our understanding of phenomena such as black holes, the fabric of space-time, and even the very nature of reality itself. The search for answers continues as scientists push the boundaries of our knowledge, ever hopeful that one day the true story of the universe's birth will be revealed. Moreover, these profound insights have the potential to completely reshape our understanding of our place in the universe. By delving into how the cosmos began and evolved, we uncover not only the origins of the universe itself, but also the intricate relationships among its various components. This understanding pushes us to question the very nature of existence and ponder the possibility of other forms of life and matter scattered across the cosmos. Could there be beings or entities out there that share a common thread with our own existence? Or are we a completely isolated phenomenon in the vast expanse of space? This exploration of the universe's infancy opens doors to some of the most profound philosophical inquiries we can face. Are we merely the product of a series of random, chaotic events that have unfolded over time? Or is there a deeper cosmic plan intricately woven into the very fabric of reality itself? As we gain clarity on the foundational moments that led to our current state, we begin to see the universe in a new light, one that sparks curiosity, awe, and wonder about the very nature of existence itself. The answers we seek could potentially redefine our role within the cosmic tapestry, offering insights into how we fit into a much larger interwoven system of life, matter, and energy. A particularly tantalizing mystery at the heart of this quest for understanding is dark matter, an invisible substance that constitutes roughly 25% of the universe. Despite its profound presence, it remains elusive, not emitting, absorbing, or reflecting light. This characteristic makes it entirely undetectable by conventional telescopes and other observational instruments. Yet, the evidence for its existence is undeniable. Scientists have deduced the presence of dark matter based on its gravitational effects on visible matter, radiation, and even the large-scale structure of the universe itself. Without dark matter, the behaviors of galaxies and other celestial phenomena would be nearly incomprehensible. Consider the rotation of galaxies as a starting point. Observations show that stars on the outer edges of galaxies are moving far too quickly to be bound by the gravitational pull of the visible mass alone. In other words, if we only accounted for the matter we can see, these stars would have long since been flung into the vast emptiness of space. However, dark matter provides the necessary gravitational force that keeps these stars in orbit. This unseen influence is crucial for the stability and formation of galaxies, and its role in shaping the cosmos cannot be overstated. Dark matter also plays an essential part in understanding the cosmic web, the intricate network of galaxy clusters and voids that defines the large-scale structure of the universe. When scientists use computer simulations to model the universe's structure, the most accurate results come from simulations that take dark matter into account. These simulations show how dark matter functions as a kind of scaffolding, providing the framework upon which galaxies form and cluster together over billions of years. This web-like structure would be unrecognizable without the presence of dark matter, which acts as the invisible force binding everything together. Yet, despite decades of research, dark matter remains one of the most profound and puzzling mysteries in cosmology. Numerous theories and candidates for dark matter have been proposed, ranging from weakly interacting massive particles, WIMP-PEEFs, to hypothetical particles known as axions. However, none of these have been definitively identified, and the true nature of dark matter remains elusive. What is certain, though, is that exploring dark matter not only brings us closer to unraveling the universe's hidden structure, but also challenges the very foundations of physics. Each new discovery, whether it's the detection of new particles or a deeper understanding of its gravitational effects, brings us one step closer to uncovering the mysteries that lie at the heart of the universe. Scientists have employed various methods to probe dark matter, each contributing valuable insights into its elusive nature. Some of the most promising approaches involve direct detection experiments, which attempt to observe dark matter particles interacting with ordinary matter. These experiments are often conducted deep underground, away from cosmic radiation that could interfere with the results. High-energy particle collisions, created in large particle accelerators like the Large Hadron Collider, are also a key tool in this search. One notable method involves the use of sophisticated detectors filled with rare gases or liquids, which are designed to capture the tiny bursts of energy released when dark matter particles collide with atomic nuclei. For instance, experiments like the Large Underground Xenon experiment and the cryogenic dark matter search are specifically designed to detect these faint energy releases, which could offer the first concrete evidence of dark matter's existence. As our search for dark matter continues, each new breakthrough brings us closer to not just understanding this enigmatic substance, but also to discovering new realms of knowledge about the cosmos itself. The journey to uncover the nature of dark matter is not just a scientific pursuit. It is a quest that has the potential to reshape our entire understanding of the universe, our place within it, and the fundamental forces that govern existence. However, the true challenge in understanding dark matter and dark energy lies in their extreme rarity and the subtlety of their effects. These elusive particles, which scientists seek to detect, are predicted to interact only very weakly with normal matter, making the task of identifying them a monumental one. It's akin to attempting to catch a whisper in the midst of a raging hurricane, barely audible, yet present. This faint interaction is why detecting dark matter directly remains one of the most difficult puzzles in modern physics. One avenue of exploration involves the study of astronomical phenomena, where scientists capitalize on the gravitational effects of dark matter. By observing the behavior of galaxies and galaxy clusters, researchers track how these massive cosmic structures behave under the influence of unseen mass. Telescopes peer into the depths of space, capturing anomalies, small but telling signs, that suggest the presence of dark matter. However, while these indirect methods offer compelling evidence for the existence of dark matter, they fail to uncover its true nature, leaving a vast chasm of uncertainty in its wake. Further complicating the search is the possibility that dark matter could consist of multiple types of particles, each with unique characteristics and interaction properties. This would necessitate a range of detection strategies, making it even harder to detect dark matter reliably. At times, experiments are set up with high hopes, only to end in failure, as the elusive particles remain undetected. These setbacks, though disheartening, reinforce the growing belief that dark matter is more complex and elusive than initially imagined. Yet, each failed attempt serves as a step forward, narrowing down the possibilities and refining the path toward eventual breakthroughs in our understanding of this cosmic enigma. In parallel with dark matter, another profound mystery looms: dark energy. This unknown force plays a crucial role in the expansion of the universe. Discovered in the late 20th century through the study of distant supernovae, scientists were stunned to realize not only that the universe was expanding, but that the expansion was accelerating. This revelation led to the identification of dark energy, a phenomenon that drives this ever-accelerating expansion. Remarkably, dark energy is believed to account for roughly 70% of the total energy content of the universe, underscoring its profound influence in cosmology. As the universe continues to expand, galaxies move away from one another, and it is dark energy that shapes this movement. Unlike ordinary matter, which tends to clump together under the influence of gravity, dark energy appears to have a repulsive effect, working against gravity itself. Instead of pulling galaxies together, dark energy pushes them apart, accelerating the rate at which the universe expands. This contrasts sharply with the early stages of the universe when gravity played a far more dominant role in slowing down the expansion. Despite its monumental influence, the true nature of dark energy remains one of the biggest unsolved puzzles in cosmology. Scientists have proposed a number of theories, with one possibility being that dark energy is a property inherent in space itself, a concept referred to as the cosmological constant. Another theory suggests that dark energy could be tied to more exotic forms of energy, potentially unlocking new realms of physics that we have yet to comprehend. Understanding dark energy is not just a matter of scientific curiosity. It could hold the key to predicting the ultimate fate of the universe. Will it continue expanding forever with galaxies racing away from each other, or will the expansion eventually slow and reverse, leading to a contraction? Around the world, researchers are actively investigating the many facets of dark energy. They are examining the cosmic microwave background radiation, studying galaxy distributions, and mapping the large-scale structure of the universe. These efforts are all aimed at gathering evidence to shed light on the characteristics of dark energy and its role in shaping the cosmos. While a full understanding of dark energy remains elusive, its presence is undeniable, and it provides an essential link between our observations of the universe and the fundamental laws of physics. It is a reminder of how much we still have to learn about the universe we call home. One of the most critical techniques scientists use to study dark energy is by measuring its influence on the expansion of the universe. Dark energy is thought to be the driving force behind the accelerated expansion, and by observing distant supernovae, astronomers can chart the rate of expansion at various stages in the history of the cosmos. These observations have confirmed that the expansion is not just occurring, but accelerating, with galaxies moving away from each other at an increasing pace. This discovery has profound implications for our understanding of the universe's fate. Another essential method involves examining the large-scale structures of the universe, such as galaxy clusters and cosmic filaments. By mapping the distribution of these structures, scientists can gain insights into how dark energy and gravity interact. The repulsive force of dark energy counteracts the gravitational pull that would otherwise cause galaxies to clump together. Using data from powerful telescopes and comprehensive surveys like the Sloan Digital Sky Survey, astronomers create detailed three-dimensional maps of the universe, tracking the evolution of galaxy clusters over time. These maps provide invaluable clues about how dark energy is influencing the distribution and behavior of galaxies. Cosmic microwave background radiation is also a vital tool in the study of dark energy. This faint relic radiation from the early universe holds information about the universe's structure and composition. By analyzing minute fluctuations in temperature across the cosmic microwave background, using instruments like the Planck satellite, scientists can infer the density and distribution of dark energy. This data, when combined with galaxy surveys, allows researchers to connect the expansion of the universe with the influence of dark energy on cosmic structures. In the ongoing pursuit to understand dark energy, researchers continue to combine observational data, simulations, and advanced mathematical models to piece together the puzzle of this enigmatic force. Though much remains unknown, the clues gathered so far have profoundly reshaped our understanding of the cosmos, guiding us closer to answers that could ultimately reveal the true nature of the universe itself. In the search for answers about the universe's deepest secrets, researchers are increasingly turning to simulations that model the evolution of the cosmos under a wide array of conditions. By adjusting factors like varying amounts of dark energy, scientists can compare these simulations with observational data, enhancing our understanding of how dark energy affects the universe. This comprehensive approach provides a richer, more nuanced view of one of the most perplexing components of the cosmos, and emphasizes the collaborative efforts of astronomers and physicists working together to unravel the mysteries surrounding dark energy. Dark matter and dark energy represent two of the most fascinating and elusive puzzles in cosmology. Despite accounting for about 95% of the universe's total mass energy content, these enigmatic forces remain invisible to all our current detection tools. Their ghostly nature is primarily due to their inability to interact with electromagnetic forces, which means they neither emit, absorb, nor reflect light. This unique characteristic forces scientists to develop alternative methods of studying these phenomena, primarily by observing their effects on visible matter instead of trying to detect them directly. Dark matter, which is believed to make up roughly 25% of the universe, is considered the structural framework that gives shape to galaxies and galaxy clusters. While it cannot be seen, its presence is inferred through its gravitational effects on the visible universe. For instance, astronomers have observed that galaxies are rotating at speeds far too high for the amount of visible mass they contain. It's as though these galaxies are surrounded by a hidden halo of unseen matter, a mystery that continues to confound scientists as they attempt to pinpoint its true nature. On the other hand, dark energy constitutes approximately 70% of the universe and is believed to be the driving force behind the accelerated expansion of the cosmos. Unlike dark matter, which exerts gravitational attraction, dark energy works in the opposite direction, pushing galaxies apart at an increasing rate. Efforts to measure dark energy largely depend on indirect observations, such as the behavior of distant supernovae and the cosmic microwave background radiation. These observations provide valuable insights into dark energy's effects, yet direct detection remains elusive. The quest to understand both dark matter and dark energy is ongoing, with physicists proposing various theories and conducting a wide range of experiments to unveil their secrets. From the latest advancements in telescope technology to specialized underground laboratories designed to capture rare particle interactions, researchers are pushing the boundaries of our knowledge. Each discovery brings us one step closer to understanding not only the composition of the universe, but also the fundamental laws of physics that govern it. As scientists continue to explore these cosmic forces, they challenge our very understanding of space, time, and reality itself. Black holes, perhaps the most enigmatic objects in the universe, lie at the heart of these mysteries, stretching our comprehension of physics and the fundamental principles that underpin the nature of reality. These cosmic behemoths are born from the collapse of massive stars, which condense matter so intensely that it creates a gravitational field so strong that nothing, not even light, can escape. This dramatic phenomenon raises profound questions about space, time, and gravity, exposing gaps in our current theoretical frameworks. At the core of each black hole lies a region known as the event horizon, a boundary beyond which nothing can escape. Once any object crosses this threshold, it is forever lost to the universe. This concept challenges our understanding of causality and time itself, forcing us to reconsider how we think about the flow of time in extreme environments. According to Einstein's theory of general relativity, time behaves very differently near a black hole, potentially stretching or bending in ways that defy our usual perceptions. Moreover, black holes present a significant challenge to two of our most well-established theories of physics: general relativity and quantum mechanics. General relativity describes gravity as the warping of space-time by mass, while quantum mechanics governs the behavior of subatomic particles. While these two theories work flawlessly within their respective domains, they begin to collide when applied to the extreme environments of black holes. This fundamental conflict leads to critical questions, such as what happens to information that falls into a black hole? Is it forever lost, or can it be recovered? The debate surrounding these questions has spurred extensive research and led to the development of groundbreaking theories, such as quantum gravity and string theory. From the supermassive black holes found at the centers of galaxies to the hypothetical primordial black holes that might have formed in the early moments after the Big Bang, these cosmic entities continue to be a focal point of scientific inquiry. Each new discovery about black holes brings us closer to answering questions that could redefine our understanding of the universe itself. The relentless pursuit of knowledge in this area not only sheds light on the behavior of the cosmos, but also offers deep insights into the fundamental nature of existence. At the very core of every black hole lies a singularity, a point where the gravitational forces become infinitely intense, and both space and time lose their usual meaning. In this region, all mass collapses into a single, infinitely dense point, and the conventional laws of physics break down entirely. The existence of singularities presents a profound challenge to our current theories of physics, particularly because they lie at the intersection of general relativity, which predicts the collapse of matter into infinite density, and quantum mechanics, which governs the behavior of the very smallest particles. The very concept of a singularity suggests that our current understanding of the universe is incomplete. It hints at the existence of new laws of physics that could unite general relativity and quantum mechanics. This is why many scientists are working toward a unified theory of quantum gravity, a framework that could provide much-needed insights into the nature of singularities. Such a theory could offer answers to questions that are not only about black holes, but also about the fundamental fabric of the universe itself, pushing the boundaries of what we know and allowing us to peek into the deepest corners of reality. The event horizon, the enigmatic boundary surrounding a black hole, continues to perplex scientists, concealing the ultimate fate of anything that dares to cross its threshold. Once past this point, conventional wisdom holds that no object, not even light itself, can escape the overwhelming gravitational pull of the singularity. Yet, what happens beyond the event horizon remains shrouded in mystery. Some scientists now challenge the prevailing idea that anything that enters a black hole is lost forever. Instead, they speculate that information might not be destroyed, but rather transformed or encoded in a way that could potentially be retrieved. This theory has sparked fierce debates as it questions the very foundation of physics by addressing the long-standing paradox of information loss in black holes. For physicists, understanding black hole singularities is not merely an academic pursuit. It is a crucial step toward unraveling some of the universe's most profound secrets. As we probe deeper into the nature of black holes, scientists hope to shed light on fundamental questions about the fabric of space-time and the evolution of the cosmos itself. With each advancement in observational technology, our capacity to uncover the truths hidden within these captivating cosmic phenomena grows ever stronger. Black holes have long captured the collective imagination, standing as both literal and metaphorical gateways into the vast, uncharted wilderness of space. Their immense gravitational pull can draw in anything that strays too close, including light, making them some of the most powerful and mysterious objects in the universe. However, the most intriguing question remains: what lies beyond the event horizon? While most theories suggest that black holes are simple cosmic traps, some bold ideas propose that black holes might act as conduits to entirely different dimensions or parallel universes. This theory introduces the possibility that a black hole could serve as a bridge between our familiar reality and realms that extend far beyond our current comprehension. One of the most exciting hypotheses to emerge is that of wormholes, hypothetical passages that could connect distant regions of space-time or even different universes altogether. If a black hole were connected to a white hole, a theoretical counterpart that expels matter, it might enable travel to distant corners of the cosmos, or perhaps even to entirely different realms of existence. This imaginative scenario raises thrilling questions. Could black holes actually be portals to places beyond our wildest dreams, offering access to distant galaxies, alternate dimensions, or realms beyond our imagination? These ideas may sound like science fiction, but they push the boundaries of what we know about space and time, urging us to think beyond the limits of our current understanding. The merger of two black holes, a colossal and increasingly common event in the universe, is another phenomenon that has captured the attention of physicists. When two black holes collide, they create not just gravitational waves, ripples in the fabric of space-time, but also a new, even more massive black hole. This newly formed black hole may have different properties than its predecessors, such as a faster spin or a more massive core, fundamentally altering the dynamics of the space around it. The energy released during these mergers is staggering, dwarfing the output of all the stars in the universe combined. While much of this energy is emitted as gravitational waves, other forms of radiation, such as gamma rays or X-rays, may also be released. This energy can have profound effects on nearby celestial objects, influencing the formation and evolution of galaxies, stars, and even the interstellar medium itself. The merger of black holes also offers a unique opportunity to explore the deepest mysteries of space-time, as these events challenge our current understanding of both general relativity and quantum mechanics. By studying the collision of these cosmic giants, scientists may gain valuable insights into the fabric of the universe itself, insights that could revolutionize our understanding of space, time, and reality. Moreover, the interaction between black holes and their surrounding environment can have even more dramatic consequences. The violent forces unleashed during a black hole merger can expel massive amounts of matter, including entire stars or gas clouds, into the surrounding cosmos. These ejections can profoundly influence the evolution of galaxies, star formation, and the distribution of matter in the universe. Each black hole merger is a unique event, one that may offer crucial clues to the nature of space-time and the ongoing evolution of the cosmos. Despite significant progress in observational technology, many of the most profound mysteries of the universe remain elusive. The sheer scale and complexity of the cosmos, with its vast array of phenomena operating under different physical laws and principles, mean that we are often confronted with new behaviors of matter and energy that defy our current understanding. As we peer deeper into the fabric of space-time, we encounter cosmic phenomena that challenge the very foundations of physics, leaving us with more questions than answers. One of the main reasons why these cosmic mysteries remain so difficult to unravel is the limitations of our observational tools. While telescopes, satellites, and other instruments have become increasingly sophisticated, they are far from perfect. Certain regions of the electromagnetic spectrum remain out of reach, hidden by cosmic dust clouds, or so distant that the light we receive reveals only a faint glimpse of the past. This means that some cosmic events and the objects responsible for them are simply beyond our ability to fully observe in real time. Furthermore, many phenomena in the universe unfold over such vast timescales, millions or even billions of years, that they are difficult for us to fully comprehend. The life cycle of stars, the interaction of galaxies, and the explosive dynamics of supernovae take place on scales that are almost incomprehensible to our human minds. As a result, there are significant gaps in our knowledge of the universe, and these gaps are not easily filled by technology alone. To truly understand the cosmic processes at work, we must continue to push the boundaries of both observation and theory, exploring new ways to probe the vast, mysterious expanse of space. Only then will we begin to unravel the deepest secrets of the cosmos, moving ever closer to understanding the true nature of our universe and our place within it. As humanity's exploration of the cosmos continues to evolve, we find ourselves standing on the edge of groundbreaking discoveries that challenge our most deeply held beliefs about the universe. With each new insight, we are reminded that our theories may not be as permanent as once thought. Concepts once considered foundational, such as dark matter and dark energy, are now forcing us to reconsider what we know and how we understand the very fabric of the cosmos. Dark matter and dark energy represent some of the greatest mysteries in modern science, and their influence on the universe's expansion raises more questions than answers. Though we have spent decades developing models that describe the universe's large-scale structure, recent findings show that our current understanding may be incomplete. For example, the accelerating expansion of the universe, a phenomenon first uncovered by astronomer Edwin Hubble in the early 20th century, continues to baffle even the most seasoned astrophysicists. What began as a simple observation that distant galaxies are moving away from us has grown into a deeper, more complex puzzle. Not only are galaxies moving away, but they are doing so at an ever-increasing rate. The discovery that this expansion is speeding up instead of slowing down suggests that something entirely outside of our current understanding of physics is responsible. At the heart of this acceleration lies a mysterious force known as dark energy, which constitutes about 70% of the universe's energy content. This enigmatic energy is thought to work in direct opposition to gravity, pushing galaxies apart and driving the universe's accelerated expansion. Yet, despite its significant influence, the exact nature of dark energy remains one of the most profound enigmas in cosmology. Some theorists suggest that dark energy may be a property inherent to space itself, while others propose it could be a dynamic field that evolves over time. Still, no theory has been able to definitively explain its behavior, and with each new discovery, we are left with even more questions than before. Adding another layer of complexity to this cosmic mystery is the presence of dark matter. Unlike ordinary matter, which emits, absorbs, or reflects light, dark matter does not interact with electromagnetic radiation in any measurable way, making it invisible to our current instruments. Nevertheless, dark matter exerts a gravitational pull on visible matter, influencing the movement of galaxies and other large structures. Although scientists have begun to develop some understanding of how dark matter interacts with the visible universe, its role in the accelerating expansion of the cosmos remains elusive. Much like dark energy, dark matter is central to the universe's accelerating expansion, yet its exact role in this phenomenon is still unclear. The quest to decipher these invisible forces is one of the most pressing challenges in cosmology today. Together, dark energy and dark matter raise fundamental questions about the nature of the universe. As we continue to probe the mysteries of these unseen forces, scientists are not merely seeking to understand the past, they are contemplating the future of the cosmos itself. How will these cosmic components shape the ultimate fate of the universe? As the universe expands ever faster, the implications for its long-term evolution become increasingly profound. Will the expansion continue indefinitely, driven by dark energy's unseen hand, or could a reversal in the rate of expansion eventually bring the cosmos to a dramatic halt? This question of fate is intricately tied to the concept of space-time, which forms the backbone of Albert Einstein's theory of relativity. Space and time, as we now understand, are not separate entities, but rather two interwoven aspects of a unified whole. While this understanding has revolutionized our approach to the cosmos, it has also led to even deeper mysteries. One of the most pressing questions is how space-time behaves at the quantum level, particularly when gravity interacts with the strange and often counterintuitive rules of quantum mechanics. These two realms, one governed by the vast sweeping effects of gravity and the other by the minute probabilistic nature of quantum physics, remain in fundamental conflict. If these two domains can be reconciled, it may unlock a new understanding of the universe's most basic laws. The universe's accelerating expansion provides yet another layer of complexity to our understanding of space-time. As galaxies move farther apart at an accelerating rate, we are forced to reconsider how space-time itself is structured and evolves. The presence of dark energy influencing the expansion of the cosmos could hold the key to understanding how space-time behaves on both large and small scales. But much like the universe itself, our knowledge of these concepts is still expanding, and many questions remain unanswered. As we explore the relationship between space-time, dark energy, and the accelerating universe, we find ourselves drawn to questions that lie at the very edge of human understanding. What is the ultimate fate of the universe? Will it continue to stretch indefinitely, growing ever colder and darker, or will it eventually reverse course, collapsing in on itself? These questions are not merely academic, they are existential. They ask us to reflect on our place in the universe and to grapple with the vast, often unfathomable nature of the cosmos. The future of cosmology depends on our ability to answer these questions. As we continue to unravel the mysteries of dark matter, dark energy, and space-time, we are reminded of how little we truly know about the universe. But it is this very uncertainty that drives scientific inquiry, pushing us to explore the unknown and to question the very fabric of reality. With each new discovery, we take another step closer to understanding the nature of the cosmos and, perhaps, the ultimate fate of everything we know. The journey of exploration and discovery is far from over. It is only just beginning. Gravitational waves, the ripples that traverse the very fabric of space-time, have emerged as one of the most profound discoveries in modern physics. These waves, generated by massive cosmic events such as the collision of black holes or the collapse of supernovae, challenge our understanding of the universe at its most fundamental level. The detection of these waves, while offering groundbreaking insights into the cosmos, has raised a cascade of questions that researchers are working tirelessly to answer. These ripples, though seemingly imperceptible, contain a wealth of information about the nature of gravity, the structure of the universe, and the very essence of space-time itself. Yet, despite the advancements, the exact mechanisms responsible for the generation of gravitational waves remain elusive. Scientists are delving into the subtle nuances of these cosmic phenomena, trying to decipher what these disturbances reveal about the laws of physics and the intricate dance of celestial bodies. As our understanding deepens, the mysteries of space-time and its pivotal role in the evolution of the universe become ever more captivating. Every discovery seems to peel back another layer of the cosmic onion, drawing us closer to understanding the universe's origins and its vast interconnected structure. But each revelation also leads to even more questions, increasing our awe and curiosity about the cosmos. The pursuit of answers to these fundamental questions is not just an academic endeavor, but a journey of existential significance. We find ourselves at a fascinating juncture where the quest to uncover the secrets of space-time, cosmic expansion, and the finite age of the universe could reshape our very understanding of existence itself. The universe, at approximately 13.8 billion years old, has been expanding ever since the Big Bang, a cataclysmic event that marked the birth of both space and time. This expansion is not merely a theoretical concept, but a tangible, observable reality. Galaxies are receding from each other, and the space between them is stretching. However, this expansion raises a significant conundrum. If the universe has been expanding for billions of years, how is it still finite in size? This seemingly paradoxical question invites a fresh perspective on the nature of the universe. To illustrate this concept, imagine the universe as a balloon being inflated. As air flows into the balloon, every point on its surface moves away from every other point, much like how galaxies are drifting apart. But unlike the surface of a balloon, the universe doesn't have an edge or boundary. It exists in a continually evolving space that is influenced by phenomena like dark energy, a mysterious force that accelerates the expansion. The concept of the observable universe, defined by the distance that light has traveled since the Big Bang, adds another layer of complexity to our understanding. This finite sphere is the limit of what we can detect, and it encompasses all that is visible from Earth. The light emitted by distant galaxies has taken billions of years to reach us, allowing us to peer back in time. But the observable universe is just a fraction of what may exist beyond our perception. The actual universe could be much larger, but potentially infinite, extending far beyond the reach of our current observational tools. As we probe deeper into these cosmic mysteries, we find ourselves grappling with the seemingly contradictory notion of a universe that is both expanding and finite. This tension between the universe's observable size and its infinite potential challenges our very conception of space and time. The expansion is not just a feature of the universe, it is the fabric of its existence. And yet it unfolds within a framework defined by its own finite age and the limits of light travel. This paradox invites us to rethink our understanding of the cosmos as we seek to reconcile the expanding universe with its observable boundaries. As we venture further into these questions, the answers we uncover not only reshape our knowledge of the universe, but also force us to confront the limits of human comprehension. One of the most intriguing and enigmatic aspects of cosmic expansion is the role of dark energy. This mysterious substance appears to pervade the entire universe, pushing galaxies apart at an accelerating rate. While scientists have made significant strides in understanding the effects of dark energy, many crucial questions remain unanswered. For instance, does dark energy remain uniform across the universe, or does it vary depending on location? The answers to such questions could dramatically alter our understanding of the forces that govern cosmic expansion. In addition to dark energy, the theory of modified gravity presents another potential explanation for the universe's accelerating expansion. While Isaac Newton's law of universal gravitation and Einstein's theory of general relativity have served as the cornerstones of our understanding of gravity, scientists are now questioning whether gravity behaves differently on cosmological scales. If new laws of physics or modifications to existing theories are discovered, they could provide an alternative explanation for the universe's expansion, potentially rewriting our entire understanding of cosmic dynamics. Beyond these theories, the existence of dark matter adds another layer of complexity to the cosmic puzzle. Although dark matter cannot be directly observed, its presence is inferred from its gravitational effects on visible matter. This unseen mass not only affects the movement of galaxies, but may also play a fundamental role in shaping the universe itself. The possibility of exotic forms of matter or energy could revolutionize our understanding, suggesting that traditional models only scratch the surface of the vast and mysterious forces at play in the cosmos. Another fascinating avenue of exploration lies in the realm of quantum mechanics. While quantum theory typically governs the behavior of particles at the smallest scales, there is growing interest in how quantum effects might influence the universe at large. Could the strange probabilistic nature of the quantum world have an impact on cosmic expansion? What might the intersection of quantum mechanics and the larger universe reveal about the true nature of reality? These are the kinds of questions that push the boundaries of our understanding and invite us to rethink everything we thought we knew about existence itself. Galaxies, the vast collections of stars, gas, dust, and dark matter, provide a rich tapestry of cosmic phenomena to explore. At the heart of nearly every galaxy lies a supermassive black hole, surrounded by a rotating disk of stars and interstellar material. This central black hole plays a crucial role in shaping the galaxy's structure, influencing the formation of spiral arms, elliptical shapes, or even irregular configurations. But a galaxy is more than just its central black hole. It is a dynamic, ever-evolving entity. The stars within galaxies come in many types, from young, hot stars burning brightly to older, cooler stars that have long since exhausted their fuel. The precise mix of stellar populations within a galaxy is determined by a multitude of factors, including the galaxy's age, its environment, and the initial conditions at the time of its formation. The evolution of galaxies is a continuous process shaped by a variety of cosmic forces. Galaxies grow by merging with others, accumulating new material, and losing parts through gravitational interactions. Star formation plays a central role in this process, driven by the availability of gas and dust. Regions of high-density gas can collapse to form new stars, while supernovae explosions scatter heavy elements back into the interstellar medium, enriching the galaxy with the building blocks of new generations of stars. This ongoing cycle of creation and destruction is what drives the evolution of galaxies, and by extension, the universe itself. As we continue to explore the cosmos, these complex processes remind us of the intricacy and interconnectedness of the universe. Each discovery we make not only reveals more about the nature of the cosmos, but also deepens our appreciation for the incredible scale of the universe and our place within it. Furthermore, the intricate relationship between dark matter and ordinary matter plays an essential role in shaping the very nature of galaxies. Dark matter's gravitational pull governs the assembly and growth of galaxies over the vast stretches of cosmic time. Despite the significant progress we've made in our understanding of galactic structure and behavior, numerous questions remain unresolved. Among these, one of the most profound is the precise function of dark energy in galaxy formation and evolution, a mystery that continues to elude our grasp. Observations strongly suggest that galaxies have evolved against the backdrop of an expanding universe, yet the underlying processes that drive their growth, behavior, and interactions during different epochs of cosmic history are far from fully understood. At the same time, scientists continue to wrestle with the nature of dark matter. This mysterious substance, which is thought to constitute a substantial portion of the universe's mass, remains undetectable through direct observation. It is only through its gravitational effects on visible matter that its presence is inferred. As astronomers develop more sophisticated instruments, such as next-generation telescopes and ambitious deep space surveys, they inch closer to uncovering the secrets of galactic composition and evolution. These ongoing investigations will gradually refine our knowledge, allowing us to pinpoint the fundamental processes that not only shape the galaxies we see, but also provide deeper insights into the universe's underlying mechanisms. The quest to understand galaxies remains far from finished, and as we continue to explore, we keep the door open to discoveries that could forever alter our understanding of cosmology. Galaxies are vast, awe-inspiring structures, each one home to billions of stars, gas, dust, and dark matter. While our understanding of how galaxies form and evolve is relatively solid, the interactions between these cosmic giants remain a source of deep intrigue. Galaxies are not solitary entities. They are part of an intricate dynamic cosmos in which they can collide, merge, and influence one another under the influence of gravitational forces. The complexity of these interactions often leads to unexpected phenomena that astronomers are still trying to fully comprehend. One of the most captivating aspects of galaxy interactions is the often chaotic and unpredictable behavior that emerges when galaxies collide. When two galaxies draw near, their immense gravitational fields can draw them into a cosmic dance. In some cases, these galaxies may pass by each other, disturbing their shapes and triggering star formation in regions that might otherwise have remained dormant. In other instances, galaxies collide and merge, resulting in the birth of a new, larger galaxy. This merger can spark spectacular bursts of star formation as the galactic material provides fresh fuel for the creation of new stars. Yet, despite these observable effects, many of the outcomes of these cosmic interactions remain a mystery. For instance, the role of dark matter during galaxy collisions is still largely unknown. Dark matter, which makes up about 85% of the universe's mass, is invisible and does not emit light, making it extremely difficult to study. Its interaction with gravity, however, suggests that it plays a critical role in shaping the structure and behavior of galaxies as they interact. Understanding how dark matter influences these collisions could provide profound insights into the nature of the universe itself. Moreover, the effects of galactic interactions unfold over immense timescales, often taking billions of years to fully manifest. This longitudinal nature adds another layer of complexity to our observations. Capturing the real-time changes that occur during such events is virtually impossible with current technology. As scientists continue to probe these awe-inspiring cosmic phenomena, they gradually piece together a narrative that not only challenges our understanding of physics, but also helps us appreciate the broader, ever-evolving story of the universe we inhabit. The vastness of the universe is a stage for powerful cosmic forces, many of which remain veiled in mystery. While our understanding of gravity, the force that binds galaxies together, is solid, there are other forces at play that significantly shape their structure. One of the most intriguing of these forces is dark matter. This enigmatic substance does not interact with electromagnetic forces, meaning it is invisible to telescopes and cannot be detected by conventional means. It is estimated that dark matter makes up about 25% of the universe's total mass and energy content, creating a gravitational framework within which visible matter can clump together to form galaxies. Another key player in the cosmic drama is dark energy, a mysterious force thought to drive the accelerated expansion of the universe, pushing galaxies away from each other. While scientists have yet to fully comprehend the nature and implications of dark energy, its presence suggests that the future structure of the universe could be vastly different from what we observe today. This could significantly affect how galaxies evolve over the course of billions of years, potentially influencing their formation, growth, and interactions in ways we have yet to fully appreciate. In addition to these mysterious forces, cosmic feedback mechanisms also play a crucial role in the structure and evolution of galaxies. Stars, particularly massive ones, produce strong stellar winds and radiation that can dramatically affect their surroundings. When these massive stars reach the end of their life cycle and explode as supernovae, they inject enormous amounts of energy and matter back into the interstellar medium. These explosive events can trigger new waves of star formation or even disrupt existing galactic structures. These stellar explosions do more than just reshape the physical makeup of galaxies. They regulate the rate at which stars are born, which in turn can influence the size and morphology of the galaxy itself. As supernovae inject matter into the surrounding environment, they may either ignite a burst of new star creation or slow down the formation process by depleting the available gas and dust. These intricate processes serve to refine the balance between creation and destruction within a galaxy, dictating its overall shape, size, and eventual fate. As scientists continue to probe these cosmic forces, they edge closer to unlocking the mysteries of galactic formation and evolution. The universe, with all its complexities and contradictions, offers an ongoing challenge to our understanding. Yet, with each new discovery, we refine our picture of the cosmos, uncovering deeper truths that guide us ever closer to the heart of the universe's grand narrative. The journey of discovery is far from over, and each new revelation brings us one step closer to comprehending the full scope of cosmic evolution. The role of supermassive black holes at the centers of galaxies is far from trivial. In fact, these colossal entities play a pivotal part in shaping the cosmos on a grand scale. Their immense gravitational fields have the power to alter the orbits of stars and reveal intricate details about how galaxies grow and evolve. These black holes are not simply passive observers of galactic life. They actively influence their environments. The powerful jets and intense radiation emitted by the material falling into these black holes can have a profound impact on star formation, regulating it across vast expanses of space. As we continue to probe the depths of the universe, we uncover new forces and interactions that stretch the boundaries of our understanding, revealing a cosmic tapestry far more intricate and expansive than we ever imagined. Each discovery hints at new layers of complexity, drawing us deeper into the mystery of the universe. Galaxies, by their very nature, do not exist in isolation. They often cluster together in groups or clusters, forming dense networks of celestial systems that are held together by gravity. However, some galaxies seem to defy this norm, existing alone in the vast, empty expanses of cosmic voids. These voids are massive regions of space where the density of galaxies is strikingly low compared to the surrounding areas. The isolation of these galaxies within such voids raises intriguing questions about the dynamics of the universe. How did these solitary galaxies end up in these empty, seemingly inhospitable places? The answer to this cosmic puzzle lies in the evolving dynamics of the universe, shaped by both gravity and the conditions set in motion by the Big Bang. In the early stages of the universe's expansion, galaxies were not as dispersed as they are today. Instead, they were initially clumped together, drawn to each other by their own gravitational attraction. However, over billions of years, the movement and interactions of these galaxies became more complex. Some galaxies found themselves separated from their original groups due to a variety of processes, including mergers and the gravitational slingshot effect. These forces ejected galaxies from their clusters, leaving them stranded in the vast emptiness of space. Additionally, the large-scale structure of the universe is anything but uniform. Some galaxies were born in less densely populated regions, places where they had little chance to interact with other galaxies. As a result, these isolated systems have remained solitary, existing far from the bustling centers of galactic activity. This phenomenon unveils the deep complexity of the universe's cosmic web, with gravity acting as a powerful architect that shapes the environments in which galaxies are formed and thrive. The cosmic web itself is a dynamic, ever-changing structure. Although voids may seem empty at first glance, they are not truly devoid of matter. Dark energy and dark matter fill these vast expanses, influencing the movement of galaxies in ways we are only beginning to understand. These mysterious forces govern the behavior of galaxies as they traverse the voids, and over time, as these voids evolve, they may occasionally give rise to a single galaxy that stands out starkly against the surrounding emptiness. This solitary galaxy serves as a reminder of the diverse and ever-shifting landscapes that make up our universe, showcasing the unpredictable and dynamic nature of cosmic evolution. The intricate interplay of forces, gravity, dark energy, dark matter, and the expansion of the universe shapes the fate of galaxies in ways we can only begin to fathom. The paths that galaxies take, the environments they inhabit, and the ways in which they evolve offer a glimpse into the complexity of the cosmos. It is as if the universe itself is a vast, living organism, constantly shifting, evolving, and reshaping itself in ways that challenge our most fundamental assumptions. As we look deeper into the universe, we realize that there is still so much we do not understand. The cosmos is a vast expanse filled with mysteries and undiscovered phenomena that could completely reshape our understanding of galaxies. Imagine galaxies functioning as intricate ecosystems, each one influenced by dynamic processes that we have yet to observe or comprehend. New celestial objects, or even entirely new forces, may exist beyond our current models, ready to expand our view of how galaxies form and evolve. Consider, for instance, dark matter, an elusive substance that constitutes a significant portion of the universe's mass. Our existing models of galaxy formation rely heavily on dark matter to explain the behavior and structure of galaxies. Yet, what if there are other types of matter or energy that we have yet to identify? The discovery of such new elements could open up entirely new pathways for galaxy formation, leading to scenarios we cannot yet imagine. These new phenomena might manifest in unexpected gravitational behaviors, strange radiation patterns, or even unusual patterns of star formation. In doing so, They could force us to rethink our most foundational theories about the nature of galaxies and the forces that govern their behavior. Moreover, the discovery of new celestial phenomena could provide us with crucial insights into the various evolutionary paths galaxies can take. Some galaxies may grow rapidly, fueled by processes we have yet to detect. Others may encounter roadblocks that stunt their growth or cause them to behave in unpredictable ways. This variability could fundamentally alter our understanding of a galaxy's life cycle, prompting us to reconsider how galaxies interact with one another across the cosmos. As we continue to probe the unknown, we realize that the universe is far more complex and unpredictable than we ever imagined. Ultimately, the discovery of these elusive phenomena would not only deepen our understanding of individual galaxies, but it would also provide a window into the larger structure of the universe itself. The vastness of our ignorance in the face of countless stars and galaxies underscores the fact that the universe holds many more secrets waiting to be uncovered. Each new discovery has the potential to shift our cosmic perspective, offering us new insights into the nature of existence itself. As we ponder the mysteries of the universe, one question looms large: does life exist beyond Earth? This question opens up a fascinating realm of possibilities. The universe is vast, containing billions of galaxies, each with billions of stars, and potentially even more planets. With the advent of new technologies, scientists have discovered thousands of exoplanets, planets orbiting stars outside our solar system. Some of these exoplanets reside in what is known as the habitable zone of their stars, where conditions may be just right for life as we understand it. Yet despite these exciting discoveries, uncertainty remains a constant companion in the quest for extraterrestrial life. One of the reasons for this uncertainty is the staggering diversity of environments across the universe. While some planets may have conditions similar to Earth, others may feature extreme temperatures, crushing pressures, or lack the essential elements required for life, such as water. The life we know has evolved under very specific conditions, making it difficult to predict what forms life might take in radically different environments. In the search for life beyond Earth, we are confronted with the immense variety of planetary conditions that exist across the universe. The possibilities are endless, and the question of whether we are alone in the cosmos remains one of the most profound and captivating mysteries in science. The exploration of this question will continue to drive our understanding of the universe, pushing the boundaries of what we know and opening new doors to the future of human discovery. The vastness of the universe, coupled with the factor of time, adds layers of complexity to our exploration of extraterrestrial life. The universe is approximately 13 billion years old, and life on Earth has existed for about 3 billion years. This immense time frame opens up the possibility that life could have emerged and perished on distant planets long before we even had the chance to observe it. It's conceivable that life once flourished in other corners of the universe, only to be lost to time, leaving behind only remnants of its existence, inaccessible to our current methods of detection. On the other hand, life may still be evolving in some faraway corner of space, but we simply lack the technology to detect its presence, at least for now. Moreover, we must consider the limitations inherent in our current approaches to searching for extraterrestrial life. Our methods predominantly focus on detecting signals or biosignatures, indicators that could suggest the presence of life on distant planets. However, these strategies are rooted in an Earth-centric understanding of what life is and how it functions. This bias, while practical, could lead us to overlook entirely new forms of life that don't conform to our conventional ideas. For example, life on other planets may not rely on carbon-based molecules, or it might exist in forms completely foreign to our biological models. As our technology advances and our understanding of biology evolves, new possibilities will inevitably emerge, keeping the question of life beyond Earth ever captivating and, for now, shrouded in uncertainty. The universe is an expansive domain, filled with extreme and often inhospitable environments. In the vast cold of space, temperatures can plummet to nearly absolute zero, while in other regions, intense heat radiates from nearby stars. These extreme conditions pose significant challenges for sustaining life as we know it. The harsh ultraviolet radiation emitted by celestial bodies, for instance, can damage DNA, making it nearly impossible for many biological organisms to survive without robust protective mechanisms. Moreover, the absence of atmosphere in outer space means there is no breathable air, and the lack of atmospheric pressure removes the protective layer that shields life on Earth from harmful cosmic radiation. Despite this, life has managed to adapt to extreme environments here on our planet, suggesting that under the right conditions, organisms could survive in other corners of the universe as well. For life to thrive on other planets, organisms may have evolved unique adaptations. These might include the ability to withstand radiation, endure extreme temperatures, or rely on subsurface water sources that are shielded from harsh surface conditions. Interestingly, scientists have been exploring Earth's most extreme environments as analogs for extraterrestrial life. Deep-sea hydrothermal vents and acidic lakes, where organisms thrive in conditions once thought to be inhospitable, provide clues about how life could adapt to harsh environments. These extremophiles, organisms that flourish in extreme conditions, offer a glimpse into how life might survive on other planetary bodies, such as the icy moons of Jupiter and Saturn, where subsurface oceans could provide a life-sustaining habitat despite the frigid exterior. These investigations not only help expand our understanding of life's potential across the universe, but also offer hope that even in the most unlikely places, life might have found a way to thrive. Yet, the search for extraterrestrial life is not solely about scanning the skies for signals or monitoring distant planets for biosignatures. At the core of this quest lies a fundamental challenge: our limited understanding of what constitutes life itself. On Earth, life is incredibly diverse, ranging from the simplest microorganisms to complex multicellular organisms. But even within this familiar framework, defining life proves elusive. Traditional criteria for life include the ability to grow, reproduce, and respond to stimuli. Yet some entities, such as viruses, blur the lines of this definition. They can reproduce, but only within a host, creating an ambiguity that complicates our ability to identify life beyond Earth. If we cannot establish a concrete definition of life, how can we recognize it in forms that may be completely different from what we know? Extraterrestrial life could thrive in environments that we cannot even imagine, possibly employing biochemistries that defy our earthbound concepts of life. This challenge is further compounded by the vast array of environments across the universe. Imagine life existing on a molten planet, in the dense, suffocating atmosphere of a gas giant, or even in the frigid oceans beneath the icy crust of a moon. Each of these scenarios raises the question, what might life look like in such conditions? Our Earth-based perspective shapes our search methodologies, potentially causing us to overlook unconventional forms of life simply because they do not fit our existing models of what life should be. As our exploration of the cosmos continues, both through technological advancements and a deeper understanding of life's many forms, the interplay between definitions and discoveries will guide us. With each new finding, from microbial life in the harshest corners of our world to the tantalizing prospects of alien atmospheres, we inch ever closer to understanding the broader tapestry of life's possibilities across the cosmos. Every question we uncover leads us deeper into the enigma of existence, challenging us to rethink our definitions and assumptions about life itself. The mystery of life in the cosmos often draws us to consider the role of unknown cosmic elements in the development of life. When we think of life's building blocks, we typically envision familiar elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the fundamental ingredients found on Earth, composing everything from our DNA to the proteins essential for cellular function. But could other unfamiliar elements be at play in distant worlds, supporting life in ways we can't yet comprehend? As we continue to explore the unknown reaches of space, the answers to these questions may reshape our understanding of life, challenging us to rethink what we consider the basic requirements for existence. However, the universe is an immense and intricate expanse, far beyond the limits of our comprehension. Its vastness and diversity suggest that the potential for life may not be confined to the elements and conditions we recognize on Earth. Astrobiologists, driven by this vast potential, hypothesize that there could be cosmic elements yet to be discovered, elements capable of creating environments conducive to life forms, unlike anything we have encountered. One of the exciting prospects is that unknown cosmic elements could catalyze the formation of life in settings starkly different from Earth's. Researchers are turning their attention to extreme environments within our own solar system. For instance, the frozen moons of Jupiter and Saturn, such as Europa and Enceladus, harbor subsurface oceans beneath their icy crusts. These moons, despite their harsh external conditions, might hold the key to life, thriving in unexpected ways. In these hidden oceans, unique chemical reactions might occur, possibly driven by new, unknown elements. These elements could set off biochemical processes essential for life, processes that would not rely on the familiar structures of organic molecules we know, but could give rise to entirely different forms of life, possibly even using alternative biochemistries. This quest for the unknown extends beyond our solar system. The study of distant exoplanets opens the door to even more extraordinary possibilities. Some of these planets may harbor environments where entirely new chemical compounds exist, compounds that could form the basis of life in ways that are currently unimaginable. Take, for instance, the high-pressure environments of gas giants. There, exotic compounds might exist, interacting in ways that could support the development of life forms fundamentally different from the organisms we recognize. These unknown elements could offer entirely new metabolic pathways, energy sources, and even survival mechanisms that sustain life in places of extreme radiation, scorching heat, or freezing cold. As our technological capabilities evolve, so too does our ability to explore these cosmic frontiers. Telescopes equipped to detect previously unknown cosmic materials, combined with missions designed to land on and sample planetary surfaces, are gradually piecing together the larger puzzle. In the not-too-distant future, we may unlock the mysteries of these far-flung realms. By identifying and understanding the role of unknown elements, we could deepen our comprehension not only of how life might take form in the cosmos, but also of the fundamental principles of chemistry and physics that govern the universe. The search for extraterrestrial life continues to awe and inspire humanity. It stretches our imagination, hinting that the potential for life is as boundless as the cosmos itself. But perhaps one of the most fascinating and perplexing aspects of this search is the ongoing investigation into the question of extraterrestrial intelligence. This pursuit, filled with mystery and intrigue, grapples with a question at its core. Do the conditions that allowed life to thrive on Earth also exist elsewhere in the universe? Astrobiologists consider numerous factors when addressing this question. Temperature, chemical composition, and the essential presence of liquid water are just a few of the conditions that might make a planet hospitable to life. Astronomers, for their part, have discovered thousands of exoplanets located within the habitable zones of their respective stars, those regions where conditions might be just right for life. Yet, despite these discoveries, we are still left with a fundamental enigma. Do any of these planets harbor life? More specifically, intelligent life. Even as our tools and methods improve, the vastness of the universe means that we have barely begun to scratch the surface of what might be out there. Another enigma that deepens this mystery is the so-called Fermi paradox. This paradox stems from a curious contradiction. Given the sheer number of stars and planets in the universe, the probability of extraterrestrial civilizations existing should be high. Yet, despite this, we have found no definitive proof of their existence, nor have we made contact with them. If intelligent civilizations are abundant throughout the cosmos, why have we not yet found any evidence of their presence? Several theories attempt to explain this paradox. Some suggest that advanced civilizations may be extremely rare, or if they do exist, short-lived. Perhaps civilizations self-destruct due to technological or societal collapse, or perhaps they fall victim to natural catastrophic events before they can develop the means to communicate across interstellar distances. Others posit that intelligent civilizations might purposely avoid us, either out of caution or indifference, leaving us in the dark about their existence. Another possibility is that the vast distances between stars make communication or interstellar travel so impractical that contact becomes almost impossible. Moreover, there is a deeper layer of complexity to the search for extraterrestrial intelligence. Our understanding of intelligence itself is fundamentally limited. Humanity tends to define intelligence through the lens of our own experience and capabilities. However, intelligence could manifest in forms completely alien to us, evolving in ways we cannot yet fathom. The kinds of cognitive processes and problem-solving abilities that we regard as markers of intelligence may be entirely different from what alien beings might possess. This raises an important question. When we search for extraterrestrial intelligence, are we even looking for the right signs? Our criteria for identifying intelligent life might be completely misguided, based on assumptions that may not hold true in a broader cosmic context. These uncertainties and paradoxes only serve to make the search for extraterrestrial life all the more captivating. As technology advances and as we explore ever more distant corners of the universe, we move closer to unraveling some of the greatest mysteries that have fascinated us for centuries. The search for life, intelligent or otherwise, is not only about finding other beings. It is about expanding our understanding of the universe, redefining what it means to be alive, and ultimately asking questions about our own place in this vast, mysterious cosmos. The silence of the cosmos remains one of the most profound and unsettling mysteries of our existence. As we stand beneath the vast expanse of the night sky, the question reverberates: are we truly alone in the universe, or are we simply not listening in the right way? With each advancement in technology, the tools to detect potential extraterrestrial signals grow more sophisticated. Yet, with every discovery, we are confronted with the broader existential questions that have lingered in the minds of humankind for centuries. What is our place in this seemingly infinite universe? As we venture deeper into the unknown, the search for extraterrestrial intelligence becomes as much a journey of self-reflection as it is of scientific discovery. In attempting to understand the cosmos, we inevitably come to understand ourselves, our limitations, and the potential for life beyond our home planet. It is a quest that transcends the scientific. It is a quest that challenges our very concept of existence. What does it mean to be alive, to be aware, to be conscious in a universe that at first glance appears empty, silent, and indifferent? Celestial objects like stars and galaxies, too, offer profound insights into the nature of life, death, and transformation. They are not static. They undergo complex and fascinating life cycles that depend on a multitude of factors: their initial mass, composition, and the environmental conditions in which they are born. A star's journey begins in a nebula, a vast, dense cloud of gas and dust that stretches across space. Over time, the force of gravity causes parts of this cloud to collapse inward, and as the pressure and temperature increase, a protostar is born. When the core of this nascent star reaches a critical temperature and pressure, nuclear fusion ignites, and the star enters the main sequence phase, a stage that can last billions of years, depending on the star's size. During this time, the star fuses hydrogen into helium, releasing vast amounts of energy in the process. This period is the longest in a star's life and is marked by stability. But as all things in the cosmos, this stage is temporary. Eventually, the star exhausts its hydrogen fuel, and the next phase of its evolution begins. For stars of smaller mass like our own sun, this involves expanding into a red giant, where the outer layers of the star balloon outward before being ejected into space, leaving behind a dense core that will become a white dwarf. This process, which can take millions of years, marks the end of the star's active life. For larger stars, the ending is far more dramatic. These stars may undergo a supernova, a colossal explosion that can outshine an entire galaxy for a brief moment in time. After the explosion, depending on the star's remaining mass, either a neutron star or a black hole may form. These cataclysmic events are well documented, but the intricacies of these transformations remain elusive. One of the most enigmatic aspects of stellar evolution is why some massive stars collapse into black holes, while others form neutron stars. This process is influenced by a variety of factors, including the star's mass, its rotation, the strength of its magnetic fields, and the nature of the mass loss that occurs throughout its life. Scientists are still working to understand the precise mechanisms that dictate these outcomes, requiring a combination of observational data and complex theoretical models. tools that remain beyond the reach of current technology. Similarly, galactic evolution holds many mysteries. Galaxies are not static. They merge, interact, and evolve over time, but the exact processes behind these events remain unclear. Of particular interest is the formation of supermassive black holes at the centers of galaxies, an enigma that has fascinated astronomers for decades. The origins of these colossal objects are still being explored, and new theories are continually emerging. One thing we do know is that dark matter, which constitutes approximately 85% of the mass of the universe, plays a critical role in the formation and behavior of galaxies. As our observational tools improve, we may finally begin to unravel the mysteries of how galaxies evolve, how they interact, and how the unseen forces of dark matter shape the universe on a cosmic scale. Cosmic time, a concept that extends far beyond the scope of our daily lives, provides an even more striking contrast to human perception. While we experience time as a continuous flow, measured in hours, days, and years, deeply intertwined with the rhythms of life, cosmic time is a measure that transcends our ordinary experience. It applies to the universe itself, stretching back some 13, if 8 billion years to the Big Bang, marking the beginning of the cosmos as we know it. Unlike the clocks we use on Earth, cosmic time takes into account the expansion of space as well as the effects of gravity. For instance, time behaves differently in different contexts. An observer far from any massive object would experience time differently than one near a black hole, where the gravitational pull warps the fabric of space-time itself. This difference in the passage of time invites profound philosophical contemplation. How do we truly measure time when our perception of it can be altered by the very fabric of the universe? Moreover, there are still many unknowns within the framework of cosmic time. The nature of dark energy and dark matter, together constituting around 95% of the universe, remains one of the most pressing questions in cosmology. Their influence on the universe's expansion and the passage of time itself is a mystery that scientists continue to explore. How does the expansion of the universe affect the flow of time, and what implications might this have for our understanding of the cosmos? These questions are not merely academic. They challenge the very way we understand reality itself. As we peer into the distant future, even more speculative scenarios arise. Could the universe continue expanding forever, eventually reaching a point where galaxies are so far apart that they can no longer interact? Or could it reverse, contracting in on itself in a process that some have called the Big Crunch? These possibilities stretch our imaginations and challenge our understanding of time, pushing us to consider what the ultimate fate of the cosmos might be. In this grand unfolding story, human life is but a fleeting moment, yet it is a moment in which we ask some of the most profound questions that have ever been posed. What is the purpose of existence? Are we alone? How do we fit into the vast and evolving tapestry of the universe? The life cycles of stars and galaxies present an even more fascinating challenge to our conventional understanding of time. While on Earth, we measure time in familiar increments, years, decades, centuries, cosmic time unfolds in a manner that defies easy comprehension. Stars live and die on scales that dwarf human lifetimes. The universe itself evolves over periods of time that span billions of years, making our everyday experience of time seem insignificant by comparison. Yet, through the study of these distant stars and galaxies, we can come to appreciate the grandeur of cosmic time, and with it, a deeper understanding of our own place in the universe. However, the cosmic clock operates on an entirely different scale, one that is almost beyond our comprehension. While human lives are measured in decades or centuries, stars exist on a timeline that spans millions, even billions of years, depending on their mass. This vast stretch of time means that events unfolding within star systems can stretch across epochs far beyond the limits of human lifetimes, urging us to reconsider our own perception of time. What might seem like the blink of an eye in human history could, in cosmic terms, be the slow, deliberate pulse of an entire star's life. When a massive star exhausts its nuclear fuel, it undergoes a dramatic transformation that culminates in a supernova, a cataclysmic explosion that marks the end of the star's existence. Yet this explosion is not merely a violent death. It is, in fact, a crucial moment in the ongoing cycle of creation. The supernova seeds the universe with essential elements such as carbon, oxygen, and iron, elements that will eventually be incorporated into new stars and planets. This continuous cycle of stellar birth, death, and rebirth can stretch across millions of years, blurring the distinctions between the past, present, and future. In this vast expanse of time, even the remnants of these explosive deaths, neutron stars or black holes, can persist for billions of years, challenging our human understanding of beginnings and endings. Planets, too, follow their own grand timelines. The formation of Earth, for example, began over 4.5 billion years ago, and the processes that shaped our planet are still unfolding today. Geological shifts, atmospheric changes, and the continual ebb and flow of nature constantly alter the face of the Earth. These ongoing processes compel us to think about time not as a simple linear progression, but as a complex web of cycles and transformations. Every layer of rock, every fossil embedded in the crust tells a story. Stories that span eons, reminding us that the environment we inhabit today is only a fleeting moment in the Earth's vast evolutionary journey. It is a reminder that our world, though familiar, is transient, constantly shaped and reshaped by the slow, deliberate forces of planetary evolution. The life cycles of celestial bodies invite us to adopt a more expansive view of time, urging us to see ourselves as part of a much larger cosmic story. Just as stars are born, live, and die, Earth, too, is caught in an ever-evolving narrative. It challenges us to think beyond the immediacy of our daily lives and to recognize our existence as a small thread in the grand, infinite tapestry of the universe. This perspective encourages deeper reflection on our place in the cosmos, asking us to embrace a sense of wonder that transcends the limits of human experience and perception. Stellar evolution, how stars are born, live, and die, is a captivating journey, one that unfolds over unimaginable stretches of time. While many of the processes that govern the life of a star remain hidden from our eyes, their impacts are profound and shape the very fabric of the universe. Stars are born in dense clouds of gas and dust, often referred to as stellar nurseries. These molecular clouds collapse under their own gravity, and from this collapse emerges a protostar. During this early phase, gravitational energy is converted into heat, raising the core's temperature until nuclear fusion ignites. This marks the beginning of a star's life. Once a star enters the main sequence phase, it spends the majority of its life fusing hydrogen into helium at its core. This fusion process releases an enormous amount of energy, creating pressure that counteracts the star's gravitational pull. This delicate balance of forces is what allows the star to remain stable for millions or billions of years. However, eventually the hydrogen in the core is depleted, and the star must undergo a series of transformations to sustain itself. For stars slightly more massive than our Sun, this leads to the fusion of helium into heavier elements such as carbon and oxygen. The death of a star when it exhausts its nuclear fuel leads to dramatic changes. Smaller stars, like our Sun, expand into red giants, shedding their outer layers and leaving behind a dense core, a white dwarf. Larger stars, however, follow a more explosive path. When a massive star's core reaches the element iron, fusion no longer produces the energy needed to counteract gravity, causing a catastrophic collapse. This collapse triggers a supernova explosion, scattering the elements forged in the star's life back into the cosmos. These elements, vital building blocks, are then available to form new stars and planets. The unseen processes that drive these transformations are not limited to gravitational forces and nuclear fusion. Stellar winds, streams of charged particles, play a crucial role in shaping a star's behavior. Radiation from the star's core interacts with its surrounding environment, influencing not only its development, but also the evolution of nearby celestial bodies. The interplay of pressure, temperature, and chemical composition governs each phase of a star's life, from its birth to its death, reflecting intricate and delicate balances. By studying these processes, scientists can decode not only the life stories of individual stars, but also the broader cosmic mechanisms that govern the universe itself. Time itself is a fundamental aspect of our understanding of the universe. It is the backdrop against which all cosmic events unfold. But time is not merely a linear progression from past to present to future. It is intricately woven into the fabric of space, forming what we now call space-time. This revolutionary concept, first articulated by Albert Einstein, fundamentally changed how we perceive motion, gravity, and the very structure of the universe. As we explore the cosmos, our understanding of time affects everything we know, from the life cycles of stars to the evolution of galaxies. The measurement of time is central to the study of the universe's history. It allows us to trace the origins of the cosmos back to the moment of its birth, known as the Big Bang. By studying the light from distant stars and galaxies, astronomers can look back in time, seeing how far that light has traveled to reach us. This gives us a unique glimpse into the early universe, revealing a dynamic and ever-evolving cosmos that has been expanding for approximately 13.8 billion years. Each moment of cosmic time provides invaluable information about celestial phenomena, their formation, and their ultimate fate. Time also plays a crucial role in predicting the future of the universe. By studying the current behavior of celestial objects, scientists can model how they will evolve over time. For example, by understanding the life cycle of stars, astronomers can predict when our sun will enter its next phase, eventually becoming a red giant, expanding and altering the entire solar system in the process. The concept of time is not confined to our present understanding of the cosmos, but extends to theories about the ultimate fate of the universe itself. Will it continue expanding forever? Will it collapse in on itself in a big crunch? Or is there some other, as yet unknown end? Time is not just a measure, it is the lens through which we explore both the past and the future of the universe. The observable universe is a remarkable concept, reflecting the boundaries of what we can currently see and measure. Spanning approximately 91 billion light-years in diameter, this sphere contains all galaxies, stars, and cosmic structures visible to human telescopes. This boundary represents the furthest reaches of our knowledge, offering us a glimpse into the vastness of the universe, but it also reminds us of the limits of our understanding. What lies beyond this boundary remains a mystery, waiting to be uncovered as our exploration of time, space, and the cosmos continues to evolve. Scientists are acutely aware that what we can observe is only a tiny fraction of the universe. Beyond what is visible to us lies an expanse shrouded in mystery, a realm that could harbor more galaxies, dark matter, and potentially phenomena so exotic that they stretch the limits of our imagination. The universe, as we understand it, may be just a glimpse of something far grander. One way to grasp the vastness of what exists beyond our current observational reach is through the concept of cosmic inflation. This theory posits that just moments after the Big Bang, the universe underwent a rapid and expansive growth, ballooning in size by a factor of millions in a fraction of a second. This immense inflation led to the universe we see today, one that is vast, nearly uniform, and still expanding. The implication here is profound. It suggests that the universe might stretch infinitely, beyond even the most far-reaching corners of our current observation. In such an infinite universe, there are regions that extend far beyond our ability to see, places where the laws of physics might operate as we understand them, or perhaps in entirely different ways. What if these distant regions harbor forms of matter and energy that we cannot yet conceive of? The notion of this boundless expanse stirs curiosity, urging us to imagine what could exist in realms so far removed from us that they remain entirely beyond our grasp. Another captivating aspect of our quest to understand the cosmos is the study of the cosmic microwave background radiation, often referred to as the relic of the early universe. This faint glow is a snapshot of the universe just moments after the Big Bang, a time when the cosmos was still in its infancy. By analyzing subtle variations in this ancient radiation, scientists are able to glean important insights into the composition, age, and expansion of the universe. Yet these observations do more than just describe what is visible to us. They raise questions about what lies beyond the edge of our observational horizon. If our universe is merely bubble within a vast multi-universal sea, each with its own set of physical laws, the implications are enormous. Could there be other universes with entirely different constants and forces of nature, potentially even more exotic than anything we could ever imagine? This hypothesis, known as the multiverse theory, opens the door to a whole new understanding of existence. The idea that there could be countless other realities, all with their own laws of physics, challenges everything we thought we knew about the cosmos. However, while the unobservable universe remains tantalizingly elusive, scientists use an array of mathematical models, computer simulations, and theoretical frameworks to try to piece together a picture of what lies beyond our current observational limits. As technology advances, our capacity to explore the universe continues to improve. Who knows what the future holds? Perhaps one day we may discover evidence that expands our understanding of the cosmos, even revealing more of what lies beyond the edge of the observable universe. Such a discovery would not only deepen our knowledge of the universe, but also inspire a greater appreciation for the complex and intricate tapestry of existence itself. One particularly intriguing phenomenon that challenges our understanding of the cosmos is the phenomenon known as dark flow. This refers to the unexpected motion of distant galaxy clusters, which appear to be moving in a particular direction, deviating from the predictions made based on the gravitational pull of visible matter and the cosmic microwave background radiation. This unusual motion suggests the presence of unseen forces or structures beyond the limits of our observation. What could be causing this? One possible explanation for dark flow is the existence of massive invisible structures located far beyond the observable universe. These structures might include enormous superclusters or vast, empty voids. If these unseen entities are made up of significant amounts of matter, they could exert a gravitational pull strong enough to influence the movement of entire galaxy clusters. If true, this would imply that the universe is far more complex than what we currently observe, hinting at the existence of hidden matter or energy that defies our current understanding of physics. In addition to the potential role of massive structures, dark flow may also be linked to the mysterious force known as dark energy. This invisible force, which is thought to be responsible for the accelerated expansion of the universe, is still largely a mystery in terms of its properties and origins. If dark energy interacts in unexpected ways with matter, it could provide an explanation for the strange motion observed in galaxy clusters. The intersection of dark flow and dark energy highlights the complexity of the forces shaping our universe, forces that remain largely invisible and elusive. Ultimately, studying phenomena like dark flow offers a pathway to exploring the vast unknowns of the universe. Every piece of evidence uncovered brings scientists closer to unraveling the mysteries of dark matter, dark energy, and the overall structure of the cosmos. As we delve deeper into these cosmic anomalies, we move ever closer to revealing a more complete picture of the universe and the hidden forces that govern it. Understanding the full scope of the universe is a grand and ambitious endeavor, but our technological limitations significantly shape the boundaries of our observations. One of the main challenges we face is the sheer vastness of space itself. The universe is not only incredibly large, but its scale operates on a level that is almost impossible for us to fully grasp in our daily lives. Even with the advanced tools we have developed, such as the Hubble Space Telescope and the James Webb Space Telescope, much of the universe remains hidden from view. These instruments primarily detect light, but there are vast regions of the electromagnetic spectrum, such as radio waves and infrared light, that may harbor critical aspects of the cosmos that we cannot detect with our current technology. Furthermore, our ability to observe distant regions of the universe is limited by the enormous distances involved. Events that take place in the farthest reaches of space take billions of years for their light to reach us, meaning that when we observe distant galaxies, we are essentially looking at them as they were billions of years ago, not as they are today. This time lag presents a challenge, as it can lead to misunderstandings about the current state of these distant objects. We are peering into the past, not the present, and this can complicate our understanding of the universe's evolution. Yet, despite these limitations, humanity continues to push the boundaries of exploration, driven by an insatiable curiosity to uncover the secrets of the cosmos. As our technology advances and our understanding deepens, we may one day be able to see farther, understand more, and possibly even glimpse the unseen realms that lie just beyond the edge of our current perceptions. The universe is vast, and within its immeasurable expanse lies a wealth of phenomena that remain largely hidden from our senses. Among these are the enigmatic black holes and dark matter, cosmic structures that emit no light, making them nearly invisible to our existing instruments. These unseen elements of the universe are not just curiosities, they are fundamental to understanding the nature of reality itself. Yet, our current observational tools, despite their sophistication, struggle to capture the full breadth of the universe's composition and dynamics. This leaves significant gaps in our knowledge, creating barriers that scientists and engineers work tirelessly to overcome. Compounding the challenge is the interference from Earth's atmosphere, which distorts the view of the stars and cosmic phenomena. Light pollution, a byproduct of modern civilization, further obscures our view of the night sky. While space-based telescopes offer a clearer perspective, they too are limited by their technological constraints, such as operational range, sensitivity, and the need for constant innovation to stay relevant. As we continue to push the boundaries of our understanding, the demand for new tools, research, and development becomes more urgent. This need for advancement fuels the dreams of scientists and engineers, driving them toward breakthroughs that could reshape our understanding of the cosmos. One such frontier is the detection of gravitational waves, ripples in space-time that could unlock entirely new ways of observing the universe. As our technological capabilities advance, we inch ever closer to unveiling the hidden mysteries of the cosmos, igniting a sense of awe and wonder about the universe's true nature. With every discovery, we come to realize that the universe is far more complex and mysterious than we had previously imagined. And with each leap in technology, we grow more aware of how much is still waiting to be uncovered. At the heart of this quest lies the desire to understand what is hidden from our view. Our current model of the universe, which relies heavily on observable phenomena such as the interactions of light, matter, and energy, is gradually being revised. We have come to accept that much of the universe is composed of unseen materials that, despite their profound impact on the cosmos, remain invisible to traditional detection methods. These materials, dark matter and dark energy, challenge the completeness of our existing understanding and open the door to new scientific revolutions. Dark matter, for instance, constitutes about 27% of the universe's total mass energy content. It doesn't emit light, nor can it be detected through traditional means. Yet its existence is inferred from its gravitational influence on visible matter and radiation. This dark, invisible mass plays a critical role in the structure and evolution of the universe, yet remains a profound mystery. If we were able to truly unlock its secrets, it would not only deepen our understanding of the cosmos, but could potentially lead to a monumental revision of our gravitational theories. We might even have to rethink the fundamental principles of physics that have stood unchallenged for centuries. Beyond dark matter, dark energy presents another profound enigma. This mysterious force is driving the accelerated expansion of the universe, contributing to approximately 70% of its total energy density. While we have observed its effects, the true nature of dark energy remains elusive. Grasping its essence could revolutionize our understanding of the cosmos, providing answers to questions about the future of the universe itself. Will it continue expanding indefinitely, or will it eventually collapse? Such questions could reshape cosmology, influencing everything from the fate of galaxies to the nature of quantum mechanics. As we peel back the layers of the universe, we find that uncovering these hidden aspects does more than just add to our knowledge. It transforms the way we view reality. The implications of understanding dark matter and dark energy extend far beyond the field of cosmology. They touch on the very nature of gravity, the fundamental forces that shape the universe, and even the conditions necessary for life to exist. Every discovery in this realm has the potential to usher in a new paradigm, one that redefines our understanding of what the universe is and how it works. One of the most profound questions in cosmology is the size and boundaries of the universe. Scientists estimate that the observable universe extends about 13.8 billion light-years in every direction from Earth, but this is only the portion of the universe we can see. What lies beyond this observable horizon remains a tantalizing mystery. Some theories suggest that the universe may be infinite, with galaxies and cosmic structures continuing indefinitely beyond our current observational reach. Others propose that the universe is finite, but its shape may curve back on itself, much like the surface of a sphere. However, these ideas remain speculative, and without concrete evidence, they remain one of the most significant unknowns in modern science. Adding complexity to this mystery is the accelerated expansion of the universe. Dark energy, which accounts for most of the universe's energy density, is driving this expansion. As a result, the more we learn about the universe, the more questions arise. Will the universe continue to expand forever, or will it eventually contract, leading to a dramatic end? These questions challenge our understanding of space, time, and the fundamental dynamics of the cosmos, inviting further exploration and deeper inquiry. Yet, even as we develop more advanced observational tools, we remain constrained by technological limitations. Much of the universe may be obscured by cosmic dust or located in regions that are inaccessible to our current instruments. As we refine our tools and push the boundaries of observation, we inch closer to answering these profound questions. However, the universe remains an elusive and tantalizing enigma, constantly inviting us to ponder its true nature and the secrets that lie just beyond our reach. Quantum mechanics, the fundamental framework that governs the behavior of subatomic particles, also plays a central role in our understanding of the universe. Its principles, such as superposition and entanglement, challenge our classical intuitions about reality, revealing a universe far stranger and more complex than we could have imagined. These principles not only reshape our understanding of individual particles, but also offer new insights into the nature of reality itself. At a larger scale, quantum mechanics governs the processes that drive the formation of stars and galaxies, as well as the creation of the elements essential for life. Within the heart of stars, nuclear fusion occurs, a process that relies on quantum tunneling, a phenomenon that allows particles to pass through barriers they would otherwise be unable to surmount. This fusion process is responsible for creating the heavy elements found in the universe, elements that are essential for the formation of planets and, ultimately, life. Without quantum mechanics, we would never have understood the processes that create the building blocks of matter, and without these building blocks, the universe as we know it would not exist. In this grand cosmic dance, quantum mechanics does more than explain the behavior of particles. It illuminates the very mechanisms that drive the evolution of the universe. As we continue to explore the deepest corners of reality, we uncover not just new facts, but entirely new ways of thinking about the cosmos. The universe is far more complex and wondrous than we ever imagined, and with each breakthrough, we inch closer to understanding the fundamental forces that shape our existence. In the vast expanse of scientific exploration, the principles of quantum mechanics emerge as not only a fundamental aspect of our understanding of the smallest particles, but also as a key that unlocks the mysteries of the universe itself. These principles are intricately woven into the fabric of cosmology, especially when we turn our attention to the early moments of the universe's existence, right after the Big Bang. During these first moments, the universe was an incredibly hot and dense quantum soup, a stage where tiny quantum fluctuations played a crucial role in shaping the distribution of matter and energy. These fluctuations, although minute at first, expanded over billions of years, laying the groundwork for the galaxies, stars, and cosmic structures that populate the universe today. In this sense, the quantum mechanics of the very early universe is not just a curiosity, it is the blueprint for the cosmos as we know it. As we probe deeper into the universe's mysteries, the intersection of quantum mechanics and gravitational physics remains one of the most significant and challenging areas of research. The quest to reconcile these two monumental theories could unlock deeper insights into the very fabric of space-time itself, offering potential answers to some of humanity's most profound and perplexing questions. Quantum mechanics, often perceived as a set of rules governing microscopic particles, reveals itself to be far more, acting as a key to understanding the grand design of the universe, shedding light on the intricate patterns that govern everything from the smallest subatomic interactions to the largest cosmic events. Yet, quantum mechanics presents some of the most profound challenges to our traditional understanding of physics. It stands in stark contrast to our classical models of gravity and relativity, which have been our guiding principles for over a century. At the heart of this conflict lies the very nature of space-time. According to Einstein's theory of general relativity, gravity is not simply a force. It is the curvature of space-time caused by mass. This theory elegantly explains how massive objects like stars and planets influence the motion of smaller objects, presenting a smooth and continuous fabric of the universe that can be modeled and predicted. Quantum mechanics, however, operates on an entirely different scale, at the level of subatomic particles, where uncertainty and probability reign. In this microscopic world, the deterministic nature of classical physics gives way to a realm where the behavior of particles is not predictable with absolute certainty, but is governed by probabilities. This fundamentally challenges the determinism at the core of classical gravity. As scientists continue to explore the quantum realm, they encounter strange and often paradoxical phenomena that seem incompatible with our established understanding of the universe. One of the most striking examples of this is the concept of black holes. In the framework of general relativity, a black hole is formed when a massive object collapses under its own gravity, creating a point where the gravitational pull is so strong that not even light can escape. However, when quantum mechanics is applied to black holes, scientists uncover paradoxes that defy easy explanation, particularly the famous information paradox. This paradox challenges one of the most fundamental tenets of quantum theory, that information, once it is encoded, is never truly lost. If matter falls into a black hole, does the information about its state vanish forever, or can it somehow be recovered? This question forces scientists to confront and rethink the very nature of information and entropy in the quantum world. Moreover, phenomena such as quantum entanglement further fuel the debate between quantum mechanics and general relativity. In entanglement, particles become linked in such a way that the state of one instantly affects the state of the other, regardless of the distance between them. Imagine two particles, like twins who share an extraordinary bond. If one twin changes in some way, the other will instantly reflect that change, no matter how far apart they are. This instantaneous connection challenges one of the core principles of relativity, that nothing can travel faster than the speed of light. Such a contradiction creates a profound rift between two of the most well-established laws of physics, drawing scientists and philosophers into a whirlwind of theoretical investigation and debate. This tension between quantum mechanics and relativity has captivated the scientific community for decades. In the search for a more unified theory, researchers are beginning to acknowledge that a new framework is needed, one that could bridge the gap between quantum mechanics and gravitational physics. The pursuit of such a theory, often referred to as quantum gravity, is at the forefront of contemporary physics. Approaches like string theory and loop quantum gravity are being explored as potential avenues for reconciling these disparate realms. These theories not only aim to harmonize the principles of quantum mechanics with general relativity, but also aspire to provide a deeper, more unified understanding of the universe, one that could reshape our perceptions of reality itself. The quest for these answers continues to intrigue and stimulate inquiry. It reminds us that the universe still holds many mysteries waiting to be unraveled. Perhaps one of the most profound phenomena that quantum mechanics introduces is quantum entanglement. This strange effect occurs when two particles become linked or entangled in such a way that the state of one particle immediately influences the state of the other, even if the two particles are separated by vast distances. This instantaneous connection between distant particles has perplexed scientists for years and raises questions that challenge the very core of our understanding of physics. When we think about quantum entanglement on a cosmic scale across the vast expanses of interstellar space, we are forced to grapple with the possibility that entangled particles could be used to communicate or share information in ways that seem to defy the traditional constraints of space and time. Could entangled particles allow for faster-than-light communication, as some theorists speculate? While this idea is intriguing, it is met with skepticism as it appears to contradict the principles of Einstein's theory of relativity, which states that nothing can travel faster than the speed of light. Nonetheless, the very concept of quantum entanglement offers tantalizing possibilities that could revolutionize our understanding of information transfer and communication on a cosmic scale. Entanglement also raises deep philosophical questions about the nature of the universe itself. If particles are linked in this way, could everything in the universe be connected at some fundamental level? Could quantum entanglement help explain some of the most mysterious phenomena in cosmology, such as dark matter and dark energy, which remain elusive despite decades of observation and study? The implications of these quantum connections extend far beyond the realm of particle physics, challenging our perceptions and urging us to reconsider the very structure of reality. As scientists continue to explore the mysteries of quantum entanglement, particularly in the context of cosmology, they are not merely seeking answers about the universe. They are delving into questions about existence itself. The bizarre and counterintuitive nature of quantum mechanics has the potential to offer a new way of understanding not just the physical universe, but the very fabric of life and the nature of consciousness. In many ways, advances in quantum physics represent the next frontier in our quest for knowledge, holding the potential to revolutionize our understanding of the fundamental laws that govern the universe. Where classical physics has described the cosmos in deterministic terms, outlining how motion and gravitation influence the behavior of macroscopic objects in a predictable manner, quantum mechanics offers a new, far more complex set of principles. These principles reveal a universe that is far more mysterious and strange than we ever imagined, challenging our deepest assumptions about reality and inviting us to explore the very edges of existence itself. However, quantum physics introduces elements of uncertainty and probability that fundamentally challenge the deterministic worldview. At the heart of quantum physics lies the concept that particles can exist in multiple states at once, a phenomenon known as superposition. For instance, an electron can be in several positions simultaneously until it is observed or measured. This counterintuitive behavior suggests that the universe may operate according to a set of rules far more complex, subtle, and interconnected than previously imagined. As researchers delve deeper into quantum mechanics, they uncover ever more intricate relationships between particles and forces that seem to defy our classical understanding of how the world works. This could mean that the very fabric of reality is more layered, nuanced, and entangled than we once thought. One of the most mind-bending discoveries is quantum entanglement, a phenomenon where particles become so deeply intertwined that the state of one instantaneously influences the state of another, regardless of the vast distance between them. This phenomenon raises profound questions about the nature of information, connectivity, and the very structure of the universe itself. If quantum entanglement extends beyond just subatomic particles into larger systems, it could challenge everything we think we know about space and time. Our current understanding of these dimensions, once thought to be fixed, might need a radical overhaul. If this notion holds true, it would suggest that the universe could be more interconnected, far more fluid, and far more bizarre than our conventional models of reality can describe. Such insights could lead to a reassessment of how we define the physical laws that govern our existence, as well as our place in the cosmos. Standing at the edge of quantum exploration, the implications of these advances could usher in groundbreaking technologies and revolutionary theoretical frameworks. These innovations have the potential not only to deepen our understanding of the cosmos, but also to fundamentally alter our conception of reality itself. By integrating quantum physics into broader scientific discussions, we may bridge gaps between various domains of physics, providing a unified understanding of the universe's workings that transcends current boundaries. Quantum mechanics operates on principles that diverge sharply from our everyday experiences, which are governed by the classical laws of physics. At the scale of tiny particles such as electrons and photons, their behavior often appears random and unpredictable, which stands in stark contrast to the orderly, deterministic nature of classical physics. This unpredictability is a direct result of the foundational tenets of quantum theory, including the intrinsic uncertainty embedded in the very structure of the universe. When we interact with these subatomic particles, the act of measurement itself disturbs their state, making precise predictions about their behavior nearly impossible. This uncertainty is famously captured by Heisenberg's uncertainty principle, which asserts that we cannot simultaneously know both the exact position and momentum of a particle with perfect accuracy. Such uncertainty is not merely a limitation of our instruments or technology, it is an inherent feature of the quantum world. While we may be able to calculate the probability of various outcomes, the specific realization of any particular event remains shrouded in uncertainty until it is observed. This fundamental unpredictability is woven into the fabric of quantum reality. As we scale up from quantum events to cosmic phenomena, the complexities multiply. In the vast expanse of the universe, countless particles and forces interact, and from this chaos, symmetry and order can emerge. This paradox highlights the unique challenge faced by classical physics, which attempts to construct a comprehensive framework for predicting large-scale events, such as the behavior of planets or the expansion of the universe. While classical models are highly effective at predicting large systems, they are unable to escape the deep-rooted randomness that governs quantum mechanics. Consequently, even though we observe trends and patterns in cosmic events, the unpredictable nature of quantum mechanics continues to influence the behavior of matter across enormous distances and vast scales. It's a constant dance between order and chaos, a reminder that the very nature of reality is far more complex than our models can fully capture. The universe, as we understand it, is a place where the laws of physics meet the randomness of quantum uncertainty. The fate of the universe, an eternal enigma, has captivated scientists for decades. Over the years, several compelling theories have emerged, each offering a different perspective on how the cosmos might evolve in the distant future. The most widely discussed of these are the theories of the Big Freeze, the Big Crunch, the Big Rip, and the possibility of a steady-state universe. Each theory provides a unique narrative on how the universe might evolve over billions or even trillions of years, painting a different picture of the universe's ultimate fate. The Big Freeze, also known as the heat death of the universe, suggests that the universe will continue to expand indefinitely. As galaxies drift further apart and stars burn out, the universe will grow increasingly colder and darker. In this scenario, matter becomes so sparse that stars and galaxies cease to exist in any recognizable form. Imagine a time, countless trillions of years in the future, when only black holes remain, slowly evaporating over incomprehensible timescales. Ultimately, this might leave behind a dark, frozen expanse, an eerie and desolate end to cosmic evolution. At the opposite end of the spectrum lies the Big Crunch hypothesis. This theory posits that the universe, after expanding for billions of years, will one day stop its outward expansion and reverse its course. The universe would then collapse back into a singular state, potentially leading to another Big Bang. This theory suggests a cyclical view of the universe, where expansion and contraction are repeated over vast cosmic timescales. While recent observations of cosmic acceleration driven by dark energy make this scenario less likely in the near future, the concept of a cyclical universe remains an intriguing and thought-provoking possibility. Then there is the Big Rip, an even more dramatic theory of cosmic demise. In this scenario, the universe's expansion accelerates to the point where galaxies, stars, planets, and even atoms are torn apart by the relentless force of dark energy. Imagine a universe in which everything, from the largest galaxies to the smallest subatomic particles, is pulled apart into an unrecognizable state of chaos. This unsettling idea paints a vivid picture of the universe's final moments, where the very fabric of existence is stretched beyond repair. Each of these theories presents a strikingly different vision of how the universe might end. Some suggest a gradual fading into nothingness, while others propose a catastrophic tearing apart of everything we know. Regardless of which scenario proves most accurate, these theories force us to confront the fragility and transience of the universe. A stark reminder that in the grand scheme of cosmic time, the fate of everything we know is uncertain and yet to be determined. The journey to comprehend the ultimate fate of the universe is an ongoing odyssey that continues to captivate the minds of scientists, theorists, and enthusiasts alike. Despite the staggering volume of evidence that keeps mounting in the realm of cosmology, several fundamental questions persist, each carrying profound implications for our understanding of cosmic evolution. As humanity ventures deeper into the mysteries of the cosmos, we are faced with questions that challenge not only our current knowledge, but the very nature of reality itself. What lies ahead for the universe? Will it keep expanding indefinitely? Could it collapse in on itself? Or is there a more elusive, perhaps unimaginable, outcome awaiting? At the heart of these questions is the enigmatic force known as dark energy. While it makes up roughly 70% of the universe, dark energy remains elusive, slipping through our grasp despite intense efforts to study it. Its mysterious properties seem to drive the accelerated expansion of the cosmos, causing galaxies to drift apart at ever-increasing speeds. Current models assume that dark energy is constant, a steady force propelling the universe's growth. But could this assumption be wrong? Could dark energy evolve, changing in intensity over time or varying with the density of the universe? If so, the future of the cosmos could look dramatically different from what we expect. One possible outcome, often referred to as the Big Rip, envisions a scenario where dark energy intensifies to such an extent that it begins tearing apart everything in its path. Galaxies, stars, planets, and even the very atoms that make up matter could be ripped asunder in a catastrophic chain reaction. But if dark energy were to weaken instead, the universe could undergo a different fate entirely. A gradual slowing of expansion followed by a dramatic collapse, leading to a big crunch, where everything in the universe collapses into an incredibly dense singularity. However, the complexities of these scenarios are compounded by the presence of dark matter, another elusive force that remains central to our understanding of the cosmos. Dark matter, which accounts for about 25% of the universe's mass, exerts a gravitational pull on visible matter, helping to shape the structure of galaxies and galaxy clusters. Yet, despite its gravitational influence, dark matter cannot be detected by conventional means. It does not emit, absorb, or reflect light, making it virtually invisible to all forms of current observation. If new discoveries shed light on its properties, how it interacts with visible matter, or how it affects the formation of galaxies, it could provide a crucial clue into determining the ultimate fate of the universe. Even more intriguing is the possibility that dark matter could play a role in altering the rate of the universe's expansion. If dark matter behaves differently than our current models suggest, it could lead to shifts in how the universe evolves. This, in turn, could drastically alter predictions about when and how the universe might reach its end, possibly opening the door to entirely new scenarios that we have yet to even consider. Meanwhile, other factors that remain unexplored, unknown forces, undiscovered particles, and even dimensions beyond the familiar three-dimensional world we live in could revolutionize our understanding of the cosmos. Theoretical physics suggests that additional dimensions or hidden fundamental forces might exist, realms we have yet to access. Any future discoveries in these areas could dramatically reshape our models of the universe, offering answers to some of the most profound questions about existence itself. These unknown variables remind us just how much remains hidden from view and how far we still have to go in our exploration of the cosmos. The universe is far from a static entity, and its evolution is guided by a web of forces and phenomena that we have only begun to scratch the surface of. Black holes, for instance, remain a mysterious force influencing the fabric of space-time, and their interaction with other cosmic elements could have far-reaching consequences for the future. Similarly, the cosmic microwave background radiation, the faint afterglow of the Big Bang, provides us with a snapshot of the early universe, offering key insights into its infancy. These phenomena, along with countless others, shape the vast and intricate cosmic tapestry, influencing the future of the universe in ways we are only beginning to understand. Ultimately, the search for answers regarding the fate of the universe involves more than just calculating distances, velocities, and expansion rates. It requires a fundamental understanding of the laws of physics as they govern the most extreme conditions, from the behavior of dark energy and dark matter to the nature of space and time itself. With each new discovery, we get a step closer to understanding not only how the universe came to be, but how it might end. Yet, predicting the future of the universe remains a daunting task, fraught with uncertainty. Despite advances in cosmology, our grasp on the forces that dictate cosmic behavior remains incomplete. We understand gravity, electromagnetism, and the nuclear forces that govern atoms, but these only form a small part of the broader picture. Dark matter, which is thought to make up a significant portion of the universe's mass, continues to evade our detection, leaving us blind to its influence. Similarly, the true nature of dark energy is still unknown, further complicating our efforts to predict the future. Moreover, the interaction between dark matter and dark energy presents another key unknown in cosmology. We know that these forces exert a powerful influence on the universe, but the extent and nature of their interplay remain a source of great mystery. Could they be working in tandem to shape the universe's fate, or are they in opposition, leading to entirely different outcomes? These are the questions that keep cosmologists up at night as they strive to piece together the puzzle of the universe's fate. In the end, the universe is a puzzle still waiting to be solved, its pieces scattered across the cosmos, just out of reach. With each new discovery, we draw closer to understanding the deeper forces that govern the cosmos and the ultimate trajectory of our universe. Until then, the mystery endures, keeping alive the wonder and intrigue of the vast and unknowable expanse that surrounds us. The future of the universe remains one of the greatest unsolved mysteries in science, and every new finding brings us one step closer to uncovering its secrets. The universe, in all its vastness, presents us with a cosmic puzzle that is not only awe-inspiring, but profoundly complex. As we peer deeper into the cosmos, we are confronted with a series of challenges that make predicting the future of the universe not only difficult, but full of uncertainty. This uncertainty stems from a variety of factors, each of which introduces its own set of complexities. First and foremost, the sheer scale and vastness of the universe introduce inherent difficulties that we can scarcely begin to comprehend. Gravitational influences, for instance, are not uniform across cosmic scales. Gravity behaves differently depending on its range, and this uneven distribution adds layers of unpredictability to the universe's dynamic nature. Furthermore, phenomena like cosmic inflation, which took place shortly after the Big Bang, continue to pose unresolved questions. Despite our best efforts, we cannot yet fully unravel the complexities of these early cosmic events, which still cast shadows of mystery as we delve deeper into the farthest reaches of space. In addition to the cosmic scale, one of the unique challenges we face when observing space is that, in essence, we are looking back in time. Light, as it travels through the universe, takes vast amounts of time to reach us. Therefore, when we observe distant galaxies, stars, and nebulae, we are actually looking at how they were millions, even billions of years ago. This temporal dimension adds another layer of difficulty in understanding the present state of the universe and the events that might affect its future. The further we look, the more fragmented and incomplete our understanding becomes. This becomes particularly evident when we consider how subtle changes in one region of space can send ripples across the cosmos, potentially altering the entire trajectory of future cosmic events, a phenomenon akin to the famous butterfly effect. The interconnectedness of celestial bodies adds another layer of complexity. Much like the chaotic behavior of weather systems on Earth, even the most seemingly insignificant variations in one celestial body's trajectory or behavior can set off a cascade of events that lead to entirely different outcomes. This means that predicting the future course of the universe is akin to predicting the future of weather systems on a vastly larger, more intricate scale. Compounding this challenge is the ever-present limitation of our observational technology. While telescopes, space probes, and other instruments have advanced exponentially in recent decades, they still provide only a limited window into the vast expanse of the cosmos. There are entire regions of space that remain invisible to our current instruments. What we know about distant galaxies, black holes, and other cosmic phenomena is often based on indirect evidence, such as gravitational effects or the way light is bent by massive objects. These indirect observations, though powerful, inherently carry a degree of uncertainty, making our ability to predict the future trajectory of the universe all the more tenuous. This uncertainty invites both wonder and curiosity. It serves as a constant reminder of how much remains unknown about the universe. Each discovery we make, whether it's the detection of a new exoplanet or the identification of previously unseen cosmic structures, opens up a new set of questions that deepen the mystery of our cosmic existence. Despite the immense strides we have made in understanding the universe, the more we learn, the more we realize just how much we still have to uncover. And yet, amid this vast sea of uncertainty, a number of potential discoveries could radically alter our understanding of the universe's future. One of the most tantalizing areas of exploration is the nature of dark energy. Thought to be the driving force behind the accelerated expansion of the universe, dark energy remains one of the greatest enigmas of modern cosmology. If scientists were to uncover its true nature or detect different forms of energy influencing cosmic expansion, it could lead to a complete reimagining of our predictions about the universe's ultimate fate. The discovery of dark energy's properties could be the key that unlocks answers to some of the most fundamental questions about the universe's past, present, and future. Similarly, the discovery of previously unknown celestial phenomena or structures could have profound implications for our understanding of the cosmos. Imagine, for instance, the identification of new types of black holes, or even exotic configurations of matter and energy. Such findings could offer breakthroughs in theoretical physics, reshaping our models of universal evolution. If we were to uncover evidence of an early universe that behaved in ways we had never anticipated, it could drastically shift our understanding of cosmic history. Perhaps one of the most profound discoveries that could reshape our cosmic perspective lies in the realm of extraterrestrial life. The search for life beyond Earth has been ongoing for decades, but definitive evidence of life, particularly intelligent life, could revolutionize not only our understanding of biology, but also our place in the universe. If humanity were to establish contact with an extraterrestrial civilization or find traces of intelligent life, it would have far-reaching consequences for how we view ourselves and our role in the broader cosmic community. Such a discovery would not merely alter our understanding of life on Earth, it would radically redefine the nature of existence itself. Finally, one of the most enigmatic relics of the early universe is the cosmic microwave background radiation. This faint radiation, which permeates the entire universe, offers a snapshot of the cosmos as it was shortly after the Big Bang. By studying this radiation in greater detail, we may be able to unravel some of the most profound mysteries of the universe's formation and its subsequent evolution. A deeper understanding of the cosmic microwave background could provide critical insights into the forces at play during the universe's earliest moments, potentially altering our predictions about its future. In each of these cases, the discoveries we make will not just add to our knowledge, they will challenge our existing paradigms and ignite our imaginations, pushing the boundaries of what we thought was possible. As we continue to explore the universe, each new revelation promises to enhance our understanding of the cosmos, providing fresh perspectives on everything from the origins of life to the fate of the universe itself. At the heart of all these cosmic phenomena is gravity, a force that governs the motions of celestial bodies, pulling objects toward each other across vast distances. This force, though weaker than other fundamental forces such as electromagnetism, has an immense impact on the structure of the universe. It shapes everything from the orbits of planets to the clustering of galaxies. Without gravity, the universe as we know it would not exist. Planets would not orbit stars, moons would not revolve around planets, and galaxies would not form. Gravity is the invisible thread that holds the fabric of the universe together, influencing the trajectory of everything within it. But gravity is not the only force at play. Other fundamental forces, such as electromagnetism and the strong and weak nuclear forces, also shape the universe in profound ways. Electromagnetism, for example, governs the interactions between charged particles, facilitating the formation of atoms and the very matter that makes up stars and planets. Meanwhile, the strong and weak nuclear forces operate on incredibly small scales, binding protons and neutrons within atomic nuclei and enabling processes like radioactive decay. These forces work together to shape not only the life cycles of individual stars, but also the evolution of galaxies over billions of years. Yet, perhaps the most mysterious forces at work are dark matter and dark energy. Though we cannot directly observe dark matter, we infer its presence from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Similarly, dark energy, believed to be responsible for the accelerating expansion of the universe, remains one of the most enigmatic phenomena in modern cosmology. Together, these unseen forces present a frontier of exploration, where conventional physics intersects with the unknown, challenging our understanding of the very nature of the universe. As we continue to study the interactions of cosmic bodies, both known and unknown forces shape the intricate choreography of the universe. With each discovery, we uncover deeper insights into the nature of the cosmos, revealing a grand design that governs everything from the smallest particles to the largest structures in existence. Our increasing understanding of these forces enriches our appreciation of the universe we inhabit and propels us further into the mysteries that lie beyond our reach. Even the seemingly straightforward events, like the collisions between celestial bodies, such as asteroids, comets, or even entire planets, remain shrouded in complexity. These high-energy events occur at such vast distances and involve such enormous scales that it becomes nearly impossible to gather real-time data. Astronomers rely on observations, simulations, and predictions, but the sheer number of variables at play makes these events difficult to fully understand. As we continue to observe and simulate these collisions, they provide us with further insight into the cosmic forces shaping the universe, but they also remind us how much we still have to learn about the complexities of the cosmos. The conditions surrounding each collision in space are far from uniform. Several factors, such as mass, velocity, and angle of impact, exert profound effects on the nature of these collisions. Take, for instance, the difference between a head-on collision between two massive asteroids and a glancing blow between a smaller asteroid and a planet. The outcomes of these interactions can vary dramatically, each presenting unique challenges and consequences. Understanding these complexities requires more than just observational data. It demands the development of sophisticated models capable of replicating the extreme conditions of interplanetary space. The variability in materials involved in these collisions adds another layer of complexity. Celestial bodies are made of diverse compositions, ranging from rocky surfaces to icy structures. When these objects collide, their behavior can differ significantly. A metallic asteroid might break apart upon impact, causing fragmentation, while a collision with an icy comet could lead to a dramatic vaporization event. These variations in physical properties necessitate extensive research and experimentation to predict how these bodies will behave under the immense forces of a collision. Moreover, the immense timescales involved in astronomical events further complicate our ability to observe and analyze these phenomena in real time. Many of these collisions unfold over millions of years, often at unimaginable distances, making direct observation nearly impossible. While each collision offers valuable insights into the workings of our solar system, the rarity and unique nature of such events means that our understanding remains incomplete. As technological advancements continue, we move closer to peeling back the layers of complexity surrounding these celestial impacts, gaining a deeper understanding of their role in shaping the evolution of our solar system. At the same time, cosmic magnetic fields are often regarded as the unseen architects of the universe. These magnetic fields extend over vast regions of space, permeating galaxies, stars, and even the intergalactic medium. They play an essential role in the formation and evolution of cosmic structures, influencing the behavior of charged particles and plasma. The interactions between magnetic fields and matter are fundamental to many astronomical phenomena, from the swirling gases in star-forming regions to the intricate patterns we observe in galaxy formations. One of the most captivating roles of cosmic magnetic fields is their influence on star formation. As clouds of gas and dust collapse under the force of gravity to form stars, Magnetic fields help regulate the flow of material. Depending on their orientation and strength, these magnetic fields can either facilitate or hinder the collapse of these clouds, affecting how quickly stars form and evolve. This process, in turn, has a profound impact on the distribution of matter in the universe. Cosmic magnetic fields are also crucial in the dynamics of accretion disks, which are found around black holes and young stars. Within these environments, magnetic fields help channel energy and angular momentum, leading to the formation of powerful jets of material that shoot out at incredible speeds. These jets not only shape the surrounding environment, but also play a role in the growth and evolution of galaxies. The energy released from these processes heats the interstellar medium, creating a complex interplay of forces that illuminates the cosmos. Beyond these smaller-scale phenomena, cosmic magnetic fields extend their influence on the larger structure of the universe. They contribute to the behavior of galaxy clusters and the cosmic web that underpins the universe's vast architecture. By providing a framework through which matter flows, magnetic fields help shape the distribution of galaxies and the large-scale structure we observe today. The ongoing study of these magnetic fields is revealing that they are not passive elements in the cosmos, but active participants in the dynamic processes that govern the universe. Cosmic radiation represents another fascinating aspect of the universe. Originating from far-reaching sources such as supernovae and active galactic nuclei, this high-energy radiation consists of protons and heavier atomic nuclei traveling through space at nearly the speed of light. When cosmic rays interact with matter, such as the Earth's atmosphere or even our own bodies, their effects can be varied and profound. Some of these interactions are well understood, while others remain cloaked in mystery. When cosmic rays collide with atoms in Earth's atmosphere, they often generate what are known as secondary particles. These secondary particles, such as muons and neutrinos, cascade downwards toward the surface. Interestingly, the majority of cosmic radiation interacts with the atmosphere rather than directly impacting the surface of the Earth. This interaction creates a complex shower of particles that can be detected by scientific instruments. While we can explain many of these processes, the full extent of the consequences and the reasons behind their specific behaviors remain areas of active research. The ongoing study of cosmic radiation continues to offer new insights, revealing just how much there still is to learn about these elusive cosmic phenomena. Cosmic radiation, in all its forms, has fascinated scientists for decades, presenting phenomena that often take them by surprise. One particularly intriguing area of study is the potential role that cosmic rays might play in cloud formation. These high-energy particles, which hail from distant regions of space, have been linked to the condensation of water vapor in Earth's atmosphere. In a way, they might be influencing the way clouds form and, by extension, impacting weather patterns and even climate itself. Yet, the exact process through which this happens remains elusive, shrouded in mystery at a molecular level. This gap in our understanding highlights just how much more there is to uncover about the interaction between cosmic rays and Earth's environment. While significant progress has been made in comprehending how cosmic radiation interacts with matter, the complexity of these interactions underscores the vastness of the unknown in our universe. As scientists delve deeper into this cosmic enigma, they are not just uncovering new facts, they are peeling back layers that could reshape our understanding of physics, our environment, and perhaps the very nature of reality itself. This continuous quest for knowledge fuels the drive of scientific inquiry, constantly evolving as we expand the boundaries of what we know. As we venture deeper into the cosmos, we uncover a web of interconnections that both surprise and intrigue. One of the most profound mysteries that has emerged in recent years revolves around dark matter and dark energy. Together, these phenomena account for about 95% of the universe, yet their true nature remains as elusive as ever. Dark matter, while invisible, exerts a powerful gravitational influence, holding galaxies together and playing a crucial role in the structure of the universe. Meanwhile, dark energy is believed to be the force responsible for the universe's accelerating expansion. Understanding these two forces will not only shed light on the architecture of the cosmos, but also answer fundamental questions about its ultimate fate. Their interplay with the matter we can observe presents a tantalizing puzzle, one that researchers are working tirelessly to solve. In parallel to the mysteries of the cosmos, scientists are increasingly focused on the connections between life, consciousness, and the universe itself. The question of how life began on Earth, and whether similar processes might have unfolded elsewhere in the universe, remains one of the most profound inquiries of our time. This line of thinking opens up fascinating possibilities about the conditions necessary for life to thrive in different environments, potentially even on distant planets. At the same time, researchers are examining the role of consciousness in shaping our perception of reality. What if consciousness is not just a product of the brain, but a fundamental aspect of the universe? This question challenges everything we thought we knew about the mind, the cosmos, and the nature of existence itself. The concept of quantum entanglement only adds another layer of intrigue to this already complex puzzle. In this strange and counterintuitive phenomenon, particles can remain entangled, connected even when separated by vast distances. This spooky action at a distance, as Albert Einstein called it, defies our traditional understanding of space and time, shaking the very foundations of classical physics. How this phenomenon works and what it might reveal about the interconnectedness of all things remains one of the most captivating areas of scientific research today. Amidst these cosmic mysteries, we are left to consider humanity's role in the grand narrative of the universe. As we accumulate knowledge about the cosmos, we are also reminded of our responsibility to protect the planet that sustains us. The destinies of humanity and the universe are intertwined in ways that may not always be immediately apparent. Our actions have far-reaching consequences, and understanding our place in the larger cosmic framework challenges us to think about the long-term impact of everything we do. This realization brings with it profound implications not just for our survival, but for the legacy we leave behind as we continue our journey of discovery. The universe, it seems, is full of enigmatic events that continue to baffle scientists and astronomers alike. One such event is the phenomenon of gamma-ray bursts. These bursts, which release extraordinary amounts of energy in the form of gamma rays, can outshine entire galaxies for brief moments in time. What makes them particularly perplexing is their unpredictability and the sheer power they unleash. While many believe that gamma-ray bursts originate from the death throes of massive stars or the collision of compact objects like neutron stars, their true origins remain a subject of intense study. Researchers are still working to decode the mechanisms behind these bursts, making them a central focus in the field of high-energy astrophysics. Equally mysterious are the forces of dark matter and dark energy, which together make up approximately 95% of the universe. Despite their immense influence on cosmic structure and expansion, the exact nature of these forces remains unknown. While scientists can observe the effects of dark matter through its gravitational pull on galaxies and clusters of galaxies, the substance itself remains invisible. It neither emits nor absorbs light, making it detectable only through its gravitational interactions. On the other hand, dark energy is believed to be responsible for the accelerated expansion of the universe, a force so elusive that it continues to defy all attempts at understanding. As researchers grapple with the complexities of these cosmic phenomena, they are left with more questions than answers, suggesting that the universe still holds many secrets. Another profound enigma lies in the behavior of black holes. While we have made great strides in understanding the fundamental mechanics of black holes, from their formation to their eventual death, much about them remains hidden beyond the event horizon. One of the most perplexing aspects of black holes is the so-called information paradox, which challenges our understanding of the laws of physics. According to classical theory, information that falls into a black hole is lost forever, yet this contradicts the principles of quantum mechanics. Will we ever reconcile the nature of black holes with our current understanding of physics? This question continues to ignite passionate debate and curiosity within the scientific community, pushing researchers to explore new ideas and theories in their quest for answers. As we continue to explore the universe, one thing becomes clear: the more we learn, the more we realize how much we still don't know. The complexities of cosmic radiation, dark matter, dark energy, black holes, and the very nature of reality itself remind us that the universe is an ever-evolving puzzle, one that we may never fully solve. Yet, the pursuit of these mysteries is what drives scientific progress, opening doors to new knowledge and deepening our understanding of the cosmos. In the vastness of space, there exist fleeting yet intensely powerful bursts of energy that confound scientists, fast radio bursts. These brief but intense flashes of radio emissions, lasting just milliseconds, release an astonishing amount of energy. Their origins remain one of the most tantalizing mysteries of modern astronomy, with theories ranging from the collision of neutron stars to potential exotic events occurring in distant galaxies. The search for answers to this cosmic enigma is still ongoing. As scientists inch closer to uncovering the source of these bursts, they are uncovering a deeper truth about the universe. There is still so much we have yet to understand. This phenomenon is a reminder that despite centuries of scientific progress, our grasp of the cosmos is far from complete. For millennia, astronomers have sought to construct models to explain the behavior and evolution of celestial bodies. They've worked to understand the fundamental laws of physics that govern everything from the smallest particles to the grandest galaxies. However, the discovery of new and unpredicted cosmic events continuously forces scientists to reevaluate their established theories. From strange bursts of energy to the sudden appearance of bizarre celestial objects, these discoveries challenge our most fundamental assumptions about the universe. Take, for example, gamma-ray bursts. These immense flashes of gamma radiation, some of the most energetic events ever observed, provide a serious challenge to existing cosmological models. Their violent outbursts can release more energy in a few seconds than our sun will emit over the course of its entire lifetime. But despite decades of research, the mechanisms behind these bursts remain largely unknown. Are they triggered by the collapse of massive stars into black holes, or are they the result of neutron-star mergers? And even if we can pinpoint the cause, these bursts present a second challenge: their unpredictability. These events often occur without warning, and their fleeting nature makes it difficult for researchers to observe them in real time. In many cases, by the time scientists detect the radiation, the event has already passed, leaving them with only fragments of data to analyze. To add to the complexity, gamma-ray bursts are not a single phenomenon, but a category of events that can be divided into two distinct types: short bursts and long bursts. Short bursts, which may be related to the merger of compact objects, and long bursts, which seem to arise from the collapse of massive stars, each have their own unique characteristics. This division only complicates the task of building a unified theory that explains all gamma-ray bursts. Scientists are still grappling with the many unanswered questions about these phenomena, and with every new discovery, new questions emerge, keeping the mystery alive. Fast radio bursts, like gamma-ray bursts, are another cosmic anomaly that has eluded easy explanation. These brief flashes of radio waves are just as intense as their gamma-ray counterparts, but are typically even more enigmatic. While the scientific community has proposed a variety of potential origins for fast radio bursts, ranging from magnetars, a type of neutron star, to supermassive black holes or even extraterrestrial civilizations, the true cause remains unknown. One of the most perplexing aspects of fast radio bursts is their extreme rarity. Despite the rapid pace of discovery, only a few dozen fast radio bursts have been observed, making it difficult to establish reliable patterns or theories. Yet, the more we learn, the more we come to realize how little we understand. For instance, the exact conditions that trigger these bursts are still not fully understood. Could the cause be linked to a single massive object, or might it be the result of an interaction between multiple cosmic entities? As astronomers continue to investigate, the idea that these bursts could be linked to catastrophic events like the merger of neutron stars or the collapse of a massive star into a black hole remains an active area of research. The distant location of these events only adds another layer of difficulty in our quest for answers. Fast radio bursts often occur billions of light years away, meaning that the light we detect is not only coming from an incredibly far-off place, but also from a time long past. This time delay means that the events we're observing may have occurred in a very different cosmic environment than the one we inhabit today. This vast distance creates complications when trying to calculate the burst's energy output, as we have no way of knowing how much energy was actually released at the source. Are these bursts common in the early universe, or are they more localized phenomena that occur at specific times? Understanding the frequency of these events could provide valuable clues about the evolution of galaxies and the formation of stars. Meanwhile, scientists are also grappling with another unexpected discovery: unusual patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. These patterns suggest that the universe may have a far more intricate structure than previously imagined, leading to debates about the very fabric of reality itself. The discovery of these patterns has sparked new lines of research into the fundamental forces of nature, particularly dark matter and dark energy, two of the most perplexing mysteries in modern cosmology. In a sense, these unpredicted cosmic phenomena, whether they are gamma-ray bursts, fast radio bursts, or anomalies in the cosmic microwave background, serve as catalysts for scientific progress. Every new discovery pushes the boundaries of our knowledge, urging scientists to reconsider long-held beliefs and theories. They force researchers to think in new ways, expanding the horizons of what is possible in the realm of cosmic study. Each discovery not only fills in some of the gaps in our understanding, but also paves the way for the next breakthrough, inspiring the next generation of astronomers and cosmologists to continue their quest to uncover the mysteries of the universe. Despite all the progress that has been made, the cosmos continues to challenge us with new and unexpected phenomena. The unknowns remain, and perhaps they always will. But it is in this mystery that the beauty of scientific exploration lies. Every unanswered question is a door to new possibilities, pushing us further into the uncharted territory of space and time, and leading us toward a greater understanding of the universe and our place within it. The immense complexity of luminous cosmic events and their lasting impact on the universe remains one of the greatest unsolved mysteries of modern science. While the intense radiation and energy released by these phenomena can be observed across vast stretches of space, scientists are still working to understand how they influence star formation in nearby regions. These dramatic occurrences, like the collision of black holes or the explosion of massive stars, are a focal point for astrophysicists eager to decipher their role in shaping the fabric of our universe. With each new discovery, a clearer understanding of these cosmic dynamics emerges, but just as many questions arise, keeping the quest for knowledge alive and vibrant. The discovery of such significant events has the potential to reshape our entire understanding of astrophysics and cosmology, challenging previously held beliefs and opening new avenues of research. Traditionally, the study of the universe has been based on well-established theories that describe phenomena like the Big Bang and the behavior of fundamental forces, theories crafted over centuries by visionaries like Isaac Newton and Albert Einstein. However, as new observations challenge these frameworks, scientists are often compelled to rethink their models and assumptions. One of the most groundbreaking observations in recent years has been the detection of gravitational waves, ripples in space-time caused by the collision of black holes. This discovery not only confirms the predictions made by Einstein's general theory of relativity, but also forces a re-evaluation of how black holes are formed and what properties they hold. These events raise further questions about the distribution of black holes in the universe, their interactions with one another, and their role in the grand narrative of cosmic evolution. Each new discovery acts as a puzzle piece, helping scientists refine existing theories or, in some cases, develop entirely new paradigms that can explain the intricacies of the cosmos. Moreover, these discoveries have the power to reveal hidden connections within the universe's structure. For example, phenomena like gamma-ray bursts or supernovae provide critical insights into the life cycles of stars and the chemical enrichment of galaxies. Understanding how these processes unfold can illuminate the mechanisms behind galaxy formation and evolution, providing a more integrated view of the universe as a dynamic, interconnected system. Every piece of data collected is like a new lens through which we gain deeper insights into the universe, helping to shape not only the theories that govern astrophysics, but also our broader appreciation of the vast and mysterious reality we inhabit. Each new revelation invites even deeper questions. What is the nature of reality? What are the origins of matter itself? Could there be unknown forces at play in the cosmos that we have yet to detect? These questions challenge the very core of human understanding, propelling the scientific community to continue its relentless pursuit of answers. Among the most compelling mysteries are the anomalies in gravitational behavior, phenomena that appear to deviate from the predictions of well-established gravitational theories. These irregularities can be observed in various contexts, such as the movement of stars within galaxies, the distribution of dark matter, and the motions of planetary bodies. When astronomers track the movement of stars in the outer reaches of galaxies, they often find that these stars are moving far faster than expected, based on visible matter alone. This discrepancy suggests that there is more to the universe than meets the eye, pointing to the existence of unseen matter and energy. This is where the concepts of dark matter and dark energy come into play. Dark matter is thought to make up a significant portion of the universe's total mass, exerting gravitational forces that influence the motion of galaxies. However, its exact nature remains elusive. The fact that our current models do not account for this invisible mass suggests that our understanding of gravity, crafted through centuries of observation and theory, may be incomplete or even incorrect in certain contexts. These gravitational anomalies compel scientists to dig deeper into the fundamental laws that govern the universe, sparking a rethinking of how mass and energy interact. One of the most telling pieces of evidence in this quest is gravitational lensing, the bending of light around massive objects. This phenomenon reveals the presence of mass in regions that we cannot directly observe, challenging traditional views of mass and energy. This has led some researchers to explore alternative frameworks, including modified gravity theories, which may better explain these perplexing observations. The gravitational anomalies we see today, though puzzling, offer a treasure trove of opportunities for discovery, each one inviting scientists to challenge established truths and uncover new aspects of the universe's deep mysteries. Gravity, despite being the most familiar of the four fundamental forces, remains one of the least understood phenomena in the universe. Every day, we experience gravity's effects when we drop objects or feel the weight of our own bodies. Yet, the fundamental nature of this force eludes us. While we can describe how gravity behaves, especially through the equations of Isaac Newton and the more recent developments of Einstein's theory of general relativity, we are still far from understanding its underlying essence. One of the reasons for this gap in our knowledge lies in the inherent complexity of gravity, especially compared to other forces such as electromagnetism, which can be observed and manipulated in controlled environments. Gravity, on the other hand, is always attractive and operates on scales that range from the tiny subatomic particles to the massive celestial bodies that govern the universe. This broad spectrum makes it difficult to isolate gravitational effects in a laboratory setting, leaving scientists to rely on indirect evidence and the observation of celestial mechanics. Moreover, gravity's refusal to align with quantum mechanics, a theory that has successfully explained the other three fundamental forces, has emerged as one of the greatest challenges in modern physics. While quantum mechanics provides a well-established framework for understanding electromagnetism, the weak nuclear force and the strong nuclear force, gravity remains stubbornly classical. This gap in understanding is one of the most profound dilemmas in contemporary physics, raising fundamental questions about the nature of space and time themselves. Scientists are exploring various theoretical models, including string theory and loop quantum gravity, in hopes of finding a unified theory that can explain all four forces in a single framework. Yet, despite decades of research, no single theory has achieved widespread acceptance within the scientific community. As the quest for a deeper understanding of gravity and the fundamental nature of the universe continues, each new discovery challenges our assumptions and brings us closer to unraveling the complexities of the cosmos. Through these discoveries, we come to appreciate not only the vastness of the universe, but also the intricacies of the forces that shape it. forces that remain largely beyond our reach, yet continue to guide the evolution of everything from the smallest particles to the grandest structures in the universe. The mystery of dark matter and dark energy presents some of the most profound challenges in modern science. These elusive entities, which account for much of the universe's unseen structure, interact with gravity in ways we still do not fully understand. Dark matter, invisible and unable to emit light, exerts a gravitational influence on the cosmos, shaping the movement of galaxies in ways that defy our current understanding. On the other hand, dark energy is thought to be the driving force behind the universe's accelerating expansion, pushing galaxies farther apart at an ever-increasing rate. The combined presence of these phenomena only deepens the enigma of gravity, a force that, despite being omnipresent, remains curiously elusive. As scientists continue to search for answers, gravity stands as a tantalizing frontier, its full nature yet to be discovered. Gravity, as we currently understand it, is one of the fundamental forces shaping the very fabric of the universe. From the largest galaxies to the smallest particles, gravity's influence is everywhere, governing how matter behaves and interacts across time and space. However, as vast as our understanding may be, the universe remains a realm of mystery, especially in regions beyond our observational reach. In these distant and inaccessible areas, gravity may not behave as we expect. One compelling possibility is the existence of unseen forms of matter and energy, dark matter and dark energy, that could affect gravity in ways we do not yet comprehend. Dark matter, for example, makes up roughly 27% of the universe. While it doesn't emit light or interact with electromagnetic forces like ordinary matter, it still exerts gravitational pull. In regions where dark matter is densely concentrated, the gravitational forces could be far stronger than what we experience in areas populated by regular matter. This could lead to significant alterations in the motion and formation of galaxies and galaxy clusters, reshaping our understanding of cosmic dynamics. Moreover, dark energy, an even more mysterious substance, appears to be the driving force behind the accelerated expansion of the universe. As it pushes galaxies apart, it alters the very structure of space itself, contributing to the cosmic landscape in ways that continue to baffle scientists. In addition to these mysterious forces, the structure of spacetime itself could vary from one part of the universe to another. According to Einstein's general theory of relativity, gravity is intimately linked with the curvature of spacetime, a curvature caused by mass. In areas with extremely high mass concentrations, such as near supermassive black holes, the curvature of spacetime can lead to gravitational effects that diverge from our standard models. The closer we get to these regions, the more gravity may behave in ways we cannot yet fully predict or understand. As we ponder these possibilities, another intriguing avenue of exploration emerges: modified theories of gravity. These theories suggest that gravity's behavior may vary depending on local conditions, such as the distribution of matter or the energy content of a particular region. Such modifications might offer new insights into how gravity operates in parts of the universe that lie far beyond our current observational reach, regions that are so distant or so remote that their gravitational behavior could be fundamentally different from what we have come to expect. The expansion of the universe itself further complicates our understanding of gravity. In regions far from our observation, the rate at which space expands could influence how gravity is experienced across immense distances. This becomes especially significant as we venture beyond the observable universe into parts of space that are fundamentally inaccessible to current technology and observation. In these regions, the density and distribution of energy could differ from what we see in our local universe, potentially leading to gravitational phenomena that contradict our current models and theories. At the heart of all these considerations lies one of the most profound questions in modern physics: how does gravity relate to the other fundamental forces of nature? While electromagnetism, the weak nuclear force, and the strong nuclear force have been successfully described by quantum mechanics, gravity remains stubbornly outside this framework. Unlike the other three forces, which act primarily at subatomic scales, gravity governs the behavior of entire galaxies and cosmic structures, making it both an incredibly powerful and deeply enigmatic force. This conceptual divide between the behavior of gravity and the other fundamental forces is a central issue in the search for a unified theory of everything, a theory that would seamlessly integrate all four forces into a single comprehensive framework. While quantum mechanics has provided an excellent description of the electromagnetic, weak and strong nuclear forces, it has yet to account for gravity. The theory of general relativity, formulated by Albert Einstein, provides a precise understanding of gravity on large scales, describing it as the curvature of space-time caused by mass. However, this theory cannot reconcile the vast differences in scale and behavior between the quantum world and the cosmic realm, leaving us with a fragmented understanding of the forces that govern the universe. Some scientists suggest that at extreme scales, such as those near black holes or during the earliest moments after the Big Bang, quantum effects might influence gravity. This gives rise to the concept of quantum gravity, which seeks to explain gravity as a fundamental interaction emerging from more basic particles or forces. The idea behind quantum gravity is that gravity might not be a continuous force at all, but rather a phenomenon that emerges from the interplay of smaller, more fundamental components. The possibility of quantum gravity has opened the door to speculative theories like string theory, which posits that the fundamental particles of the universe are actually tiny, vibrating strings. These strings could, in theory, unify gravity with the other forces at incredibly small scales, offering a new way to think about the connections between them. As researchers continue to investigate this relationship, they face not only theoretical challenges, but also practical obstacles. Experimental evidence is crucial to advancing our understanding of gravity's role in the universe, and scientists are hopeful that breakthroughs may come from high-energy particle collisions or from observing extreme cosmic phenomena where gravity's effects are unmistakably strong. Each new discovery, no matter how small, brings us one step closer to understanding the mysterious bond between gravity and the other forces, and it holds the potential to revolutionize our understanding of the universe itself. The gravitational influence of objects, meanwhile, extends far beyond the regions we can currently measure. As described by Einstein's general theory of relativity, gravity is not an instantaneous force acting at a distance. Rather, it is the bending of space-time caused by mass. Every object with mass, whether a planet, star, or galaxy, creates a curve in space-time around it, forming a gravitational field that affects everything in its vicinity. Even objects that are far away from the source of gravity feel its effects, though these influences may be incredibly subtle. This becomes particularly intriguing when we consider how gravitational waves propagate across the universe. These ripples in space-time, caused by the movement of massive objects such as neutron stars or black holes, travel at the speed of light. Over vast distances, they subtly alter the motion of objects, often in ways that remain undetectable until observed by sensitive instruments. In fact, gravitational waves can travel for billions of light years, carrying the signature of cosmic events long after the objects that caused them have moved on. Gravity is one of the most fundamental forces in the universe, holding galaxies, stars, and even entire clusters together across vast distances. Its influence extends far beyond what we can directly observe, shaping the large-scale structure of the cosmos in ways that are often unseen. For example, massive structures like galaxy clusters exert a gravitational pull that reaches well beyond their visible limits. This unseen force is believed to be influenced by dark matter, a mysterious form of matter that does not emit light and can only be detected through its gravitational effects. Although dark matter remains elusive, its gravitational pull is crucial in shaping the formation and movement of galaxies, suggesting that there is much more to the universe than meets the eye. Even though we cannot directly observe dark matter, its gravitational influence is undeniable, revealing the hidden forces at work on a cosmic scale. Understanding how gravity works in these expansive contexts has always been limited by the precision of our instruments and the methodologies available to us. But as technology advances, there is potential for us to gain deeper insights into the far-reaching effects of gravity, perhaps revealing new aspects of the universe we've never considered before. As we continue to measure and study gravity, we find that it leads to deeper questions about the very nature of the force itself. the more we learn, the more we realize there is still so much we do not understand, especially as we venture deeper into the cosmos. With every new discovery, the mysteries of the universe unfold further, hinting at astonishing revelations that could completely reshape our understanding of the universe. Light, in contrast, serves as one of our most vital tools in unraveling these mysteries. When we observe celestial bodies, we are not only gazing at distant objects, we are observing light that has traveled across vast stretches of space, carrying crucial information about the universe. This light contains details about the composition, temperature, motion, and even the distance of stars and galaxies, all of which help us piece together the history of the cosmos. By studying various wavelengths of light, ranging from visible to ultraviolet to infrared, we can decode much about the nature of the universe. For instance, the light emitted by a star reveals its chemical makeup, allowing astronomers to determine its components, such as hydrogen, helium, and heavier elements. Light itself can even provide clues to a star's age and evolutionary path, adding another layer of understanding to our cosmic exploration. But what makes light even more fascinating is how it changes over time. As light travels across the expanding universe, it stretches and shifts, a phenomenon known as redshift. This change in the wavelength of light acts as a cosmic clock, allowing scientists to measure the speed at which galaxies are moving away from us and providing insight into the rate at which the universe itself is expanding. This expanding universe also led to one of the most groundbreaking discoveries in modern cosmology. The universe's expansion is accelerating. This unexpected revelation has fueled theories about dark energy, a mysterious force that is believed to be driving this acceleration. Yet, for all the incredible information that light offers, it also has its limitations. Although it allows us to learn so much, light can only reveal part of the cosmic story. Certain phenomena, such as black holes, do not emit light at all, making them extremely difficult to study using conventional optical means. Moreover, the universe is full of interstellar dust and gas clouds that absorb or scatter light, obstructing our view of distant celestial objects. Even more frustratingly, the Earth's atmosphere distorts the properties of light before it reaches us, adding noise to our observations. To mitigate these challenges, astronomers have turned to space-based observatories, which operate above the atmosphere, providing us with clearer, unobstructed views of the cosmos. Yet, despite all of this, light alone is not enough to give us a full understanding of the universe. To truly grasp the scope of the cosmos, scientists must combine what we learn from light with other methods of observation. Gravitational waves and cosmic microwave background radiation, two other fundamental tools in our cosmic toolkit, allow us to gather more complete information about the universe's structure, its past, and its future. Together, these methods offer a more comprehensive picture of the universe, one that sheds light on its deepest mysteries. Light also often reveals the secrets of the universe's behavior, particularly how it interacts with gravity. One of the most fascinating phenomena related to light is gravitational lensing. When light passes near massive objects such as black holes or clusters of galaxies, its path bends due to the gravitational pull of these objects. This bending of light creates a natural lens that magnifies distant objects, allowing astronomers to view parts of the universe that would otherwise be hidden. This distortion of light gives us a unique opportunity to study objects far beyond our direct line of sight and even observe the universe in ways that were previously impossible. Another cosmic mystery is the way light behaves as it travels vast distances. As light moves away from us, it undergoes redshift, which is the stretching of light into longer wavelengths as a result of the universe's expansion. This shift not only helps us track the movement of galaxies, but also raises fundamental questions about the future of the cosmos. Is the universe destined to expand forever, or could it one day collapse back in on itself in a dramatic, cataclysmic event? As we continue to study the redshift of light, we edge closer to understanding the ultimate fate of the universe itself. However, the universe is not simply a collection of objects that emit light in visible wavelengths. Many astronomical bodies emit light in more obscure parts of the electromagnetic spectrum, such as gamma rays or radio waves. These wavelengths hold critical clues about the universe, yet they remain difficult to observe due to the limitations of current technology. For instance, some wavelengths are absorbed or scattered by particles in space before they even reach us. Others, like those emitted by pulsars or gamma-ray bursts, are often far beyond the range of our current telescopes. Furthermore, some objects emit light primarily in specific wavelengths, making them harder to detect. Yet, as technology progresses, so does our ability to perceive these elusive signals. New detectors and advanced techniques are constantly being developed, promising to expand our observational reach and uncover hidden corners of the universe that have remained out of sight. Each new advance brings us one step closer to uncovering the full spectrum of cosmic phenomena and deepening our understanding of the universe. Light, often celebrated for its role as the fastest traveler in the universe, is more than just a messenger. It is a key that unlocks mysteries about the very nature of the universe, its history, and its future. As it journeys across the vastness of space, light not only reveals what is visible, but also opens doors to new questions about reality itself. Through light, we explore the cosmos, but as we continue to refine our methods of observation, we may yet uncover even more astonishing secrets about the universe's behavior and its underlying forces. Light, in its many forms, is far more than a simple phenomenon we observe with our eyes. It is, in essence, a messenger, one that travels vast distances across the cosmos, carrying with it secrets of the universe. Each interaction light undergoes, from its journey through space to the subtle transformations it experiences, hints at the existence of forces and variables far beyond our immediate understanding. It's these intricate relationships hidden within the behavior of light that challenge our perceptions and continually push the boundaries of scientific exploration. For instance, light's polarization offers more than just an optical illusion. It can provide deep insights into the magnetic fields in space, pointing to forces that shape the cosmos in ways we are only beginning to grasp. Meanwhile, the intensity of light, the very brightness that reaches our telescopes, holds clues about the distribution of matter in the universe. Each shift in light, every transformation and reflection, carries with it fragments of information about the mechanics of the universe itself. But beyond these observable clues, there is a deeper, more philosophical essence to light, an essential thread that connects the very fabric of space and time. As it journeys through the vast expanse of the cosmos, light acts as both a guide and a recorder. It captures the history and composition of celestial bodies, encoding them in a form we can decode. But the path of light is not always as clear as we might hope. The universe is full of mysteries, dark matter, dark energy, and even unknown cosmic structures that can drastically alter the signals we receive, distorting our understanding of what is out there. These unseen forces shape the very way light interacts with space. When light travels from distant galaxies to our telescopes, it is not a straightforward journey. Along the way, it encounters numerous interstellar obstacles. Cosmic dust, for instance, can scatter or absorb certain wavelengths, muddying the clarity of the signal. More complex still is the phenomenon known as gravitational lensing, where massive objects like galaxies or black holes bend light around them, creating multiple images of the same distant object. This bending of light presents significant challenges in our quest to measure distances and determine the true nature of far-off objects. If we fail to recognize these cosmic influences, we risk misinterpreting the data we receive, leading us to conclusions that may be far from accurate. Then, there is the matter of dark matter and dark energy, two elusive forces that remain largely invisible to our instruments. Although we cannot directly see or detect them, these mysterious components exert profound influence over the cosmos. Dark matter, for example, has a gravitational pull that affects the motion of galaxies, while dark energy drives the accelerated expansion of the universe itself. If these forces are not taken into account when we analyze light from distant sources, our calculations about the expansion rate of the universe or the mass of galaxy clusters could be wildly off base. The interplay between light and the unknown forces of the universe continuously reminds us of the intricacy of the cosmos. Every new discovery, whether through the study of light's interactions with cosmic phenomena or through the unveiling of new structures, adds a layer of complexity to our understanding. forcing us to reconsider long-held assumptions. With each revelation, we gain new insights, and in turn, our interpretations of the universe shift, refining our knowledge and challenging our perceptions of what is truly out there. Light is not merely a tool. It is a bridge between the visible and the invisible, between what we can observe and what we can only imagine. When we observe the light emitted or reflected by distant celestial bodies, we are not just gazing at those objects themselves. Instead, we are interpreting the light that reaches us after traveling unimaginable distances across the universe, picking up pieces of information about their composition, temperature, density, and even motion along the way. This makes light one of the most valuable instruments in the astronomer's toolkit, enabling us to learn about distant stars, galaxies, and other cosmic wonders without ever leaving our home planet. One of the most powerful techniques that scientists use to study light is spectroscopy. In this method, light from stars, galaxies, or other celestial bodies is dispersed through a prism, splitting it into its constituent colors. Each color represents a different wavelength of light, and each element in the universe absorbs and emits light at unique wavelengths, much like a fingerprint. By analyzing these spectral lines, scientists can determine the chemical composition of far-off stars or galaxies, even as they remain light years away. This technique reveals a wealth of information: the elements present, their relative abundances, and how matter is interacting across vast cosmic distances. Furthermore, light's role extends to mapping the large-scale structure of the universe itself. When we observe the light from distant galaxies, we are not just looking at those galaxies as they exist in the present moment. We are peering into the past, as the light we see now began its journey millions or even billions of years ago. This allows astronomers to trace the evolution of the cosmos, helping to map out the so-called cosmic web, a vast network of galaxies, galaxy clusters, and dark matter that stretches across space. The light we receive is not just a snapshot of what exists today, but a glimpse into the universe as it was in its distant past. Gravitational lensing further enriches our understanding of the universe's structure. When light from a background object is bent around a massive foreground object, it not only distorts the image, but also offers insight into the distribution of dark matter. Though dark matter itself does not emit light, its presence can be inferred by observing how it influences the motion of visible matter. Gravitational lensing thus serves as a cosmic magnifying glass, allowing scientists to map the unseen and uncover hidden structures that would otherwise remain undetectable. In this never-ending quest for knowledge, light serves as both a tool and a symbol, a key to unlocking the mysteries of the universe. Through its intricate dance with cosmic forces, it continually reshapes our understanding of the cosmos, urging us to look deeper, question further, and embrace the complexity of the universe in all its wonder. Advancements in technology have unlocked new doors for exploring the vast unknowns of the universe, allowing scientists to peer further into the cosmos than ever before. Space telescopes, equipped with advanced imaging technologies, can now capture light from the faintest and most distant objects. These include ancient galaxies formed shortly after the Big Bang, shining with the faint light they emitted billions of years ago. Instruments like the Hubble Space Telescope have played a pivotal role in gathering invaluable data, transforming our understanding of the universe's early structure and its evolution over eons. Through the power of light, we are slowly unraveling the deepest mysteries of the cosmos. Each beam of light from these ancient objects provides insights into the hidden wonders of the universe, revealing the intricate details of its formation and ongoing development. As we peer deeper into space, we are able to explore not just the grand cosmic structure, but also the very fabric of existence itself, helping us piece together the vast, interconnected story of everything that is. One of the most pressing challenges we now face is the growing issue of cosmic debris. Often referred to as space junk, this debris consists of everything from minuscule paint flecks to massive defunct satellites and spent rocket stages. The accumulation of such debris is the direct result of an ever-expanding human presence in space, compounded by natural collisions and the gradual breakdown of celestial bodies. Yet, what remains largely unknown is how various types of space debris interact with each other and the space environment at large. The role of solar radiation and micrometeoroid impacts in these interactions is crucial yet poorly understood. These environmental factors can significantly alter the trajectories of debris or even damage its structural integrity, leading to unpredictable outcomes. The effects of space weather, combined with the physical collisions between debris particles, can produce a chaotic environment that is difficult to predict. This unpredictability makes space debris a major concern for future space missions, as the risks of collision increase with each new object that joins the orbital mix. Equally significant is the influence of gravitational forces exerted by larger celestial bodies, such as planets, moons, and even the Sun. These forces can disrupt the orbits of space debris, pushing it into unstable trajectories, or conversely, capturing it into a steady orbit. However, these gravitational interactions are often far more complex than initially believed. The gravitational dynamics governing the movement of cosmic debris are still a mystery in many respects, and scientists are only beginning to understand the chaotic behaviors that can arise as debris moves through space. Some debris may encounter gravitational forces that send it on unpredictable paths, increasing the chances of collisions with other objects. The composition of space debris plays a significant role in determining how it behaves under the harsh conditions of space. Different materials, whether metal, plastic, or ceramic, react uniquely to the extreme environmental factors present in orbit. For instance, metallic debris may withstand impacts better than plastic fragments, which could disintegrate upon collision. These differences lead to varying rates of decay and accumulation in orbit. Yet, despite decades of research, there are still many unknowns regarding how different materials interact with the harsh conditions of space. Understanding these behaviors remains a critical challenge, driving ongoing investigations into how space debris evolves and the best ways to manage it. Moreover, human activity in space presents its own set of complications when it comes to managing debris. The growing number of satellites and other space missions has introduced a new layer of complexity to the space environment. Although efforts to reduce space junk are underway, such as the implementation of end-of-life decommissioning protocols for satellites, these initiatives are still imperfect and not universally enforced. The lack of global agreements on how to manage space debris further exacerbates the issue, leaving many unknowns in its wake. As our ventures into space continue to deepen, understanding and addressing these unknown factors will be critical, not only for the safety of future missions, but also for the long-term health of the orbital environment. The challenges don't end there. Throughout the cosmos, there are numerous celestial phenomena that continue to defy our understanding of the universe. Some of these anomalies, such as fast radio bursts, dark matter, and the behavior of certain galaxies, seem to operate outside the boundaries of established physical laws. These mysterious occurrences challenge the very foundations of physics and have prompted scientists to rethink and revise our current models of the cosmos. One of the most puzzling phenomena is dark matter, which makes up approximately 27% of the universe, yet remains invisible to our detection instruments. While its gravitational effects can be observed in the rotation of galaxies and the way galaxy clusters move, its true nature continues to elude scientists. Dark matter's elusive nature leaves many questions unanswered, as scientists are left to ponder how such a dominant component of the universe can remain so fundamentally undetectable. Similarly, fast radio bursts, brief but extremely powerful flashes of radio frequency, have added another layer of mystery. First discovered in the early 21st century, these bursts were initially thought to be signals from extraterrestrial civilizations. However, their true origins remain a subject of intense debate and investigation. The phenomenon continues to elude explanation, forcing scientists to reconsider their assumptions about the nature of the universe. These bursts are a striking reminder of the limitations of our current models and the need for an adaptable scientific framework capable of integrating new discoveries that challenge our existing knowledge. The persistence of these anomalies underscores the complexity of the universe itself. As we continue to explore the farthest reaches of space, we are confronted with questions that current theories simply cannot answer. Whether it's the nature of dark matter or the cause of fast radio bursts, these discoveries force us to recognize that our understanding of the universe is still far from complete. They serve as a reminder that science is a dynamic, evolving process, one that must remain open to new data and ideas that have the potential to expand or completely overhaul our current understanding of reality. The more we discover, the more we realize just how much remains to be uncovered. And in the face of these cosmic mysteries, our curiosity and thirst for knowledge will continue to drive the quest for answers, no matter how elusive they may seem. The universe is a vast and incredibly dynamic entity, one whose complexities we are constantly striving to understand. As we push the boundaries of human knowledge, the tools we use to study the cosmos are evolving at an extraordinary pace. Every time we develop a new telescope or perfect an analytical method, we unveil new data that has the potential to confirm existing theories or challenge them entirely. These revelations, often unexpected and strange, serve as poignant reminders of how much we have yet to learn. In many respects, these anomalies act as stepping stones in our relentless pursuit of knowledge, fueling our curiosity and igniting a passion to deepen our comprehension of the universe. They push us to ask questions, explore new ideas, and never settle for the answers we already have. Each unexplained phenomenon we encounter shines a light on the beauty and complexity of the cosmos, captivating both scientists and enthusiasts alike. Through the lens of these anomalies, the universe becomes not just a subject of study, but a realm of endless possibilities, where each new discovery beckons with the promise of something greater. But as we venture into this unknown, one of the core challenges in scientific research, especially in the fields of astronomy and cosmology, lies in distinguishing between anomalies and artifacts of observation. An anomaly is an unexpected result or observation that defies our current understanding of the universe. It's a signal, a piece of data that doesn't quite fit into the neatly defined theories we have so far. Anomalies can suggest the presence of new phenomena or indicate that our models of the universe need substantial revision. In contrast, an artifact of observation is a misleading result caused by limitations or errors in the tools or methods used to collect data. These artifacts, while often mistaken for genuine discoveries, are ultimately a product of the imperfection inherent in our observational technology and techniques. The process of differentiating between a true anomaly and an artifact of observation is rigorous and requires an array of scientific methods. Researchers approach this challenge with an analytical mindset, examining the data from as many angles and perspectives as possible. For example, if a peculiar signal is detected from a distant star, astronomers don't simply accept it at face value. They analyze the signal across a range of wavelengths and times to see if it behaves consistently, or whether it fades away after adjusting for instrument noise and environmental factors. This meticulous process helps determine whether the observation is a genuine anomaly or the result of some error or interference. Replicability is another cornerstone of this investigation. Anomalies that persist across different instruments and observational setups tend to receive more attention. If a unique signal is captured by one telescope, scientists will check if similar data is obtained from other telescopes or through different methods of observation. If the same phenomenon is detected consistently across multiple platforms, it increases the likelihood that what's being observed is, indeed, a genuine anomaly rather than a mere fluke or artifact. Perhaps most crucially, the scientific community itself plays an indispensable role in validating these observations. Peer review and collaborative analysis are integral to ensuring that conclusions drawn from any new discovery are solid and reliable. When researchers share their findings, they invite scrutiny from other experts who can identify potential biases, errors, or alternative explanations. This collaborative process is what ensures that science, by its very nature, remains self-correcting and that our understanding of the universe is always evolving. It is a constant reminder that, while we may know more today than we did yesterday, the boundaries of our knowledge are always shifting, urging us to question what we know and challenge what we think we understand. In this ever-expanding realm of discovery, cosmic dust plays an unexpectedly vital role. Often overlooked as mere debris scattered throughout space, these tiny particles have profound implications for the formation and behavior of celestial bodies. Comprised of elements such as carbon, silicate, and iron, cosmic dust can be formed from a variety of sources, including dying stars, supernova explosions, and the remnants of comets. However, far from being insignificant, these particles are fundamental building blocks of the universe, influencing everything from star formation to the dynamics of galaxies. One of the most intriguing aspects of cosmic dust is its role in the birth of stars. When vast clouds of gas collapse under their own gravitational pull, the presence of dust particles provides a surface for gas molecules to clump together. This clumping process is what initiates the formation of new stars. Without the dust, star formation would likely occur in a very different manner, potentially limiting the variety and types of stars and planets that could emerge in the universe. Dust also affects the temperature of these gas clouds, absorbing energy and facilitating further collapse, which ultimately leads to the creation of new stars. Moreover, cosmic dust doesn't just contribute to star formation. It also plays a crucial role in how we observe the universe. As light from distant stars and galaxies travels through space, it encounters these particles which scatter and absorb the light. This process, known as extinction, causes celestial objects to appear dimmer and redder than they truly are. While this phenomenon presents challenges in our ability to accurately measure and understand distant objects, it also serves as a powerful tool. By studying the effects of dust on the light that passes through it, astronomers can learn more about the distribution and composition of cosmic dust itself, gaining insights into the very fabric of the universe. In a broader sense, the recycling of cosmic dust through the death of stars and their subsequent explosions as supernova forms part of a grand cycle in the universe. When stars reach the end of their life cycles, they expel dust and other materials into the surrounding space, enriching the interstellar medium with essential elements. This process of destruction and rebirth has far-reaching implications, influencing everything from chemical composition of new stars to the potential for life on newly formed planets. As scientists delve deeper into the study of cosmic dust, we are only beginning to grasp the true scope of its impact on the universe's grand design. Similarly, space debris, often thought of as nothing more than the remnants of human activities, offers a fascinating glimpse into both the history of space exploration and the underlying forces that govern the cosmos. Space debris includes a wide range of objects, from old satellites and spent rocket stages to fragments from collisions between space objects. While often dismissed as mere clutter, space debris can provide valuable insights into the dynamics of celestial bodies and the processes that shape our solar system. By analyzing space debris, scientists can uncover important data about the forces at play in Earth's low orbit and beyond. The distribution and composition of space debris reveal patterns that are influenced by gravitational interactions and other cosmic forces. These forces, detectable on Earth, are the same ones that shape the orbits of larger celestial bodies, such as asteroids and comets. By studying the behavior of space debris, astronomers can refine their understanding of these larger cosmic forces and develop more accurate models of the space environment. Each fragment of space debris carries its own unique signature, offering clues about its origin and trajectory, thus enabling scientists to improve their models of both artificial and natural space dynamics. Through this analysis, we gain not only a deeper understanding of the history of human space exploration, but also a more profound comprehension of the universe's underlying laws and interactions. Far from being insignificant remnants, space debris acts as a mirror that reflects the cosmic processes governing everything from the birth of stars to the orbits of asteroids. In this way, space debris, like cosmic dust, becomes an invaluable tool in our ongoing quest to understand the universe. As we delve deeper into the phenomena of space, a fascinating narrative unfolds before us, one that connects the seemingly small, often overlooked details of human-made objects in orbit with the grand movements of the universe. One of the most telling features of this story comes from observing the collisions between objects in orbit around Earth. These seemingly inconsequential impacts offer us an invaluable window into how various materials behave in extreme conditions, providing a rare glimpse into the resilience and limitations of materials when subjected to the harsh realities of space. However, the significance of these space collisions reaches far beyond the immediate understanding of debris and materials science. By analyzing these events, researchers can begin to draw crucial connections with cosmic phenomena. For example, the impact of meteoroids on planetary surfaces shares fundamental similarities with the collisions between space debris. These cosmic events, which are often seen as distant, can be linked directly to the actions humans take in Earth's orbit. In doing so, we gain a clearer understanding of how planetary atmospheres and surfaces react over time to these relentless impacts. In the context of space debris, these collisions offer more than just data on material behavior. They serve as a bridge between the microcosm of human activity and the macrocosm of celestial forces. Through the study of debris impacts, scientists can begin to make meaningful comparisons between space activities and the larger scale events that shape the universe. This comparison underscores the interconnectedness of all things, from the tiniest fragments of debris to the largest celestial bodies. By observing these connections, we come to appreciate how human actions, even those that seem insignificant, are inextricably linked to the broader processes of the cosmos. This growing understanding of space debris, and the role it plays in both the immediate and distant future, reveals the broader narrative of our universe. The debris, with its constant movement and interactions, functions both as a historical record and as an active participant in the ongoing evolution of space. Through this lens, space debris becomes more than just the remnants of human activity. It becomes a key player in the story of the universe itself. At the heart of this understanding lie the universal constants, those fundamental quantities that define the very fabric of our universe. These constants, which remain steadfast throughout space and time, are crucial in shaping the laws of nature. Among the most well-known of these constants are the speed of light in a vacuum, the gravitational constant, and Planck's constant. Each of these constants is pivotal in a wide range of scientific fields, from cosmology to quantum mechanics, and they form the bedrock upon which much of modern physics is built. Through these constants, scientists are able to make predictions, form hypotheses, and create theories about the behavior of matter and energy in the cosmos. Yet, despite their critical importance, the precise values of these constants are still the subject of much debate and research. While the speed of light is generally accepted to be approximately 300,000 kilometers per second, subtle variations in measurement techniques can lead to slight differences in our understanding of this fundamental value. One reason for these discrepancies is the complex nature of the experiments used to determine these constants. The methods employed to measure them can vary in precision, leading to different interpretations of the data. Additionally, the potential for new physics beyond our current understanding also plays a significant role. As we uncover new phenomena in the universe, certain constants may prove to be more flexible or subject to change than we previously believed. For instance, theories that attempt to unify gravity with the other fundamental forces of nature, or those that address the mysteries of dark matter and dark energy, often bring into question the constancy of the gravitational constant itself. The pursuit of a precise understanding of these universal constants is not just a scientific endeavor. It is a journey toward unraveling the deeper truths of reality. With each discovery, scientists are forced to reevaluate their theories, refine their models, and push the boundaries of knowledge further. The interplay between measurement, theory, and discovery keeps the field of physics vibrant and ever-evolving, drawing us ever closer to the heart of the universe's most profound mysteries. In cosmology, we often regard certain aspects of the universe as immutable, such as the laws of physics or the speed of light. These principles seem stable and predictable, providing the foundation upon which much of our understanding is built. However, the possibility of yet undiscovered variables in the cosmos challenges these assumptions. Hidden forces, particles, or phenomena may exist that we have yet to detect, and their discovery could lead to revolutionary shifts in our understanding of the universe. If such an unknown variable were to be identified, it could dramatically alter our equations and models. What we once thought of as fixed and unchanging principles might reveal themselves to be more malleable than we ever imagined. Take, for instance, the ongoing mystery surrounding dark matter and dark energy. These elusive entities, which are believed to make up most of the universe's mass and energy, remain largely unknown. However, a breakthrough in our understanding of them could redefine how we perceive the universe's expansion and overall structure. Such discoveries are not limited to the realm of dark matter and dark energy. New phenomena could fundamentally reshape our understanding of space and time itself. Concepts like the cosmic microwave background, the faint glow of radiation left over from the Big Bang, could turn out to be more dynamic than previously thought. With each anomaly that doesn't fit neatly into existing theories, scientists are prompted to reconsider their models, searching for new explanations and paradigms. This unyielding pursuit of knowledge brings us ever closer to the true nature of the universe. The mysteries that lie beyond our current comprehension hold the potential to transform our understanding in profound ways. Each new insight challenges our assumptions and enriches our grasp of the cosmos, revealing layers of complexity that we have yet to fully appreciate. As we strive to unlock the secrets of the universe, our understanding of the universal constants remains a cornerstone of our scientific endeavor. These constants, like the speed of light, the gravitational constant, and Planck's constant, are fundamental to how we interpret the universe. They allow scientists to refine their theories and deepen their understanding of the interactions between matter and energy across the cosmos. For example, the precise value of Planck's constant is essential in the field of quantum mechanics, influencing everything from particle behavior to the development of cutting-edge technologies like lasers and semiconductors. Meanwhile, the speed of light remains a cornerstone of Einstein's theory of relativity, shaping our understanding of space and time. These constants, while seemingly fixed, are still the subject of ongoing exploration. As we continue to push the boundaries of our knowledge, we are reminded that the universe is far from fully understood. With every discovery, we move one step closer to uncovering the full depth of its mysteries. These constants possess far-reaching consequences, revealing clues about the very nature of the universe and the fundamental principles that govern it. The idea that these constants could vary challenges our most foundational understandings of physics, hinting that perhaps our current models and assumptions may need significant revision. This possibility raises profound questions for scientists, urging them to rethink the very fabric of reality and the forces that shape it. It pushes us to examine not only the known laws of nature, but also the unexplored territories that could offer new insights into the workings of the cosmos. At its core, the study of these constants underscores the unity and predictability of the physical world. They are the bedrock upon which our theories are built, helping to ensure that our scientific framework remains tethered to reality. As we gain a deeper understanding of these constants, we reinforce the consistency of our physical laws and, in turn, open doors for technological advancements that improve human life. Our ability to harness these constants shapes everything from the most mundane technologies to the most groundbreaking scientific discoveries, each step bringing us closer to understanding the universe's true design. The potential to discover new constants in physics is a gateway to revolutionary change. These constants are not mere numbers. They are the very values that guide how matter and energy interact across the universe. When a new constant is identified, it offers scientists the chance to re-examine existing theories that describe how the universe operates. This new information could prompt fresh interpretations of both large-scale cosmic phenomena and the minute workings of subatomic particles. For example, the introduction of a new constant might point to previously undiscovered forces or interactions that govern the fabric of reality itself. It could challenge well-established ideas like Einstein's theory of general relativity or the Standard Model of particle physics. Such a discovery could set the stage for a more unified theory of everything, a goal that has long eluded physicists who seek to bridge the gap between gravity, electromagnetism, and quantum mechanics. Additionally, the discovery of new constants could offer unexpected insights into some of the universe's most mysterious and enigmatic features. Dark matter and dark energy, which together account for the majority of the universe's mass and energy content, are still largely unknown. The integration of new constants could help explain these phenomena, offering a clearer picture of how the cosmos works at its deepest level. It could even reshape our understanding of the universe's ultimate fate and evolution, presenting new questions we hadn't even considered before. Beyond the realm of physical science, the discovery of new constants holds deep philosophical implications. It forces us to confront the vastness and complexity of the universe, reminding us that we have only begun to scratch the surface in our quest for knowledge. Every new constant uncovered is a reminder that the universe is far more intricate and mysterious than we might ever fully comprehend. It challenges us to reimagine our place within it and to embrace the limitless possibilities that await us in the pursuit of understanding. However, measuring these fundamental constants across the immense expanse of space presents a host of challenges. One of the most significant hurdles is the sheer scale of the distances involved. Take, for instance, the light from distant stars, some of which are millions or even billions of light years away. As light travels such staggering distances, its properties can change, leading to potential distortions that make it harder for scientists to obtain accurate measurements of the constants. The precision of our measuring instruments also plays a crucial role. While modern technology has allowed us to develop sophisticated tools capable of detecting cosmic phenomena, these instruments still have limitations. Cosmic environments are far from uniform, and factors like interstellar dust, gravitational fields, and electromagnetic radiation from distant objects can all interfere with our ability to capture the true nature of the constants we are studying. These factors create noise in the data, making it difficult to isolate the signals we need. Moreover, some constants, such as the speed of light or the gravitational constant, may appear to vary depending on the local conditions or the specific environments in which they are measured. For example, near black holes, where gravitational forces are extraordinarily strong, the expected behaviors of light and time can differ significantly from what we observe in more familiar settings. This variability adds complexity to our understanding of these constants and their role in shaping the cosmos. The immense span of time that the universe has existed, approximately 13.8 billion years, also introduces complications in our measurements. The conditions that prevailed in the early universe may differ substantially from those we observe today. This means that any variations in the constants we measure might be influenced by the ongoing evolution of the cosmos rather than reflecting a static reality. The interplay between time, distance, the limitations of our instruments, and the diverse conditions of the universe creates a challenging landscape for scientists striving to understand the fundamental constants that govern reality. One of the most perplexing puzzles in cosmology is the imbalance between matter and antimatter. According to theoretical models, the Big Bang should have produced equal amounts of both matter and antimatter. However, as we observe the universe around us, it is overwhelmingly composed of matter, with only a tiny fraction of antimatter present. This discrepancy raises an intriguing question. Where has all the antimatter gone? Antimatter consists of particles that are the mirror image of the particles that make up ordinary matter, but with opposite charges. For every particle of matter, there exists a corresponding antiparticle. When matter and antimatter meet, they annihilate each other, releasing energy in the process. This phenomenon is described by Einstein's famous equation E=mc². Given that the observable universe contains almost no antimatter, scientists have been grappling with the question of why this symmetry has been broken. One leading theory is that in the early universe, conditions favored the creation of matter over antimatter. This process, known as baryogenesis, suggests that certain mechanisms may have led to a slight excess of baryons, particles that make up protons and neutrons, allowing matter to dominate. However, the precise details of baryogenesis remain elusive, and no definitive explanation has yet been found. This imbalance between matter and antimatter is more than just a curiosity. It is a critical piece of the puzzle in understanding the universe's origins and evolution. As scientists continue to explore this mystery, They may uncover new insights that could reshape our understanding of the cosmos, challenging existing models and opening new doors to the nature of the universe itself. In the ongoing pursuit of unraveling the mysteries of the cosmos, experiments aimed at studying antimatter in controlled settings, such as particle accelerators, have revealed crucial insights. These experiments have shown that under many conditions, antimatter behaves strikingly similarly to matter, yet subtle differences persist. These variations could potentially hold the key to one of the most profound mysteries of the universe, the imbalance between matter and antimatter. As scientists continue their exploration of these asymmetries, they hope to shed light on the cosmic imbalance that has shaped the very fabric of the universe. This quest is not just a scientific endeavor. It has become a captivating journey that stirs the imagination of both researchers and enthusiasts. It promises to uncover hidden truths about the fundamental nature of reality itself, offering a deeper understanding of how the universe came to be and what forces govern its structure. One of the most glaring asymmetries we observe is the difference in behavior between matter and antimatter. According to current theories, during the Big Bang, nearly equal amounts of matter and antimatter were created. However, as we gaze upon the universe today, it is overwhelmingly dominated by matter. The question remains, why does antimatter appear to be so scarce in comparison? This absence of antimatter has profound implications, not just for our understanding of the universe, but for the fundamental laws of physics themselves. The standard model of particle physics, despite its wide success in explaining many phenomena, fails to account for why we observe more matter than antimatter. This discrepancy hints at the presence of unknown forces or yet to be discovered particles that could provide the missing pieces of the puzzle. Researchers are focusing on phenomena such as CP violation, which refers to the differences in the behavior of particles and their corresponding antiparticles. By investigating these phenomena, scientists hope to uncover deeper truths that could change our understanding of the universe's structure and its origins. The implications of this matter-antimatter asymmetry extend far beyond the realm of particle physics. It has deep ramifications in cosmology, particularly regarding the formation of stars, galaxies, and planets. Without this imbalance, the universe would be a vastly different place. Rather than the rich, structured cosmos we see today, we might find ourselves in a universe dominated by high-energy photon fields where matter could never coalesce into stars and galaxies. This asymmetry, then, can be viewed as a fundamental cornerstone in the cosmic tapestry, enabling the formation of the intricate structures that define our universe. Furthermore, understanding this asymmetry is critical for our theories about the ultimate fate of the universe. Current models suggest that if the universe had evolved differently, perhaps if our understanding of dark matter or dark energy were altered, the future could take an entirely different path. We might find ourselves in a universe governed by different laws, one that challenges our very comprehension of existence. This possibility underscores the importance of studying the intricate interplay between matter, antimatter, and the fundamental laws that govern the cosmos. Symmetry plays a crucial role in our understanding of the universe, influencing not only its formation but also its evolution over time. In physics and cosmology, symmetry refers to the idea that certain properties of objects or systems remain unchanged under specific transformations or conditions. This principle is essential for deciphering the laws that govern the universe, from the smallest particles to the largest structures. In the moments immediately following the Big Bang, the universe was in a highly symmetrical state. This symmetry allowed energy and matter to spread evenly throughout the cosmos. However, as the universe expanded and cooled, various forms of symmetry began to break down. This breakdown led to the creation of distinct particles and forces, ultimately shaping the matter that makes up stars, galaxies, and planets. Without these changes in symmetry, the vast and varied structures we see today simply would not exist. Symmetry continues to play a vital role in modern theoretical physics. For example, the principles of gauge symmetry form the basis of our understanding of the fundamental forces of nature. These principles dictate how particles interact and give rise to forces like electromagnetism and gravity. When symmetries are preserved in these interactions, they determine the predictable patterns we observe throughout the universe. From the formation of atoms to the behavior of distant galaxies, symmetry provides the foundation for the laws that govern the cosmos. However, not all symmetries predicted by theoretical models have been observed in the universe. This raises intriguing questions about the fundamental nature of reality and the underlying framework of the cosmos. One possible explanation for the absence of certain symmetries is the phenomenon of symmetry breaking. While symmetries may exist at a fundamental level, the universe has undergone various phases of evolution that have transformed these perfect symmetrical states into more chaotic, asymmetric conditions. A familiar analogy is that of a snowflake falling apart as it descends from the sky. Once perfect, it becomes fragmented as it interacts with the surrounding environment. In particle physics, symmetry breaking is thought to explain why certain particles, such as the massless photon and the massive W and Z bosons, emerge from this process. The events that led to symmetry breaking in the early universe may also account for why we don't observe certain predicted particles or interactions linked to these symmetries today. Another factor that could explain the lack of observed symmetries is that they might operate at energy scales that are currently beyond our reach. The universe is vast, and the energy levels required to detect certain phenomena may only be achievable through new advancements in technology, such as more powerful particle accelerators. For instance, the Higgs boson, a particle central to the Standard Model, was only confirmed in 2012 after being theorized for decades. It serves as a reminder that our understanding of the universe is always evolving, and there may still be particles and forces that we have yet to uncover. As scientists continue their exploration of the cosmos, they remain hopeful that new experimental conditions will eventually allow us to detect phenomena that could revolutionize our understanding of the universe and its underlying symmetries. The study of symmetry and asymmetry is not just an academic pursuit, and it is a journey that touches upon the very nature of reality itself. As researchers delve deeper into these concepts, they continue to shed light on the evolving tapestry of existence, revealing insights that will shape our understanding of the universe for generations to come. Whether through theoretical models or experimental discoveries, the search for symmetry and its breakdown remains one of the most exciting frontiers in modern physics. Moreover, some symmetries within the universe may be inherently fragile, existing only under specific and often rare conditions. In a cosmos as dynamic and ever-evolving as ours, it is conceivable that the initial conditions required to manifest certain symmetrical properties faded away long ago. As the universe expanded and cooled over billions of years, the environment in which fundamental particles operate transformed drastically. The delicate balance that once supported some symmetries disappeared into the mists of time, leaving them as relics of a forgotten past. Unraveling these mysteries lies at the cutting edge of modern physics and continues to push the boundaries of our understanding of the universe. The concept of cosmic symmetry is a fascinating one within the field of cosmology. It suggests that, on grand scales, the universe exhibits uniformities and patterns that transcend local phenomena, extending across vast distances. Yet, despite its elegance, the forces that govern this symmetry remain largely enigmatic. The quest to decipher these forces and understand the underlying principles of cosmic symmetry propels physicists towards several intriguing avenues of inquiry. This pursuit is most notably centered in the realms of particle physics and theoretical physics. One potential key to understanding cosmic symmetry lies in the fundamental interactions that govern the universe's behavior. These interactions include gravity, electromagnetism, and the strong and weak nuclear forces. Each of these fundamental forces operates according to its own set of symmetry principles. For instance, the symmetry of electromagnetic interactions is governed by gauge theory, a framework suggesting that these forces arise from the very structure of space and time itself. If we can decode how these fundamental forces relate to the overarching cosmic symmetry, we may unlock secrets about the very fabric of reality. Further complicating the picture are the theoretical frameworks like string theory, which propose that hidden dimensions exist beyond the three we experience in everyday life. These extra dimensions, which are undetectable at human scales, could hold the answers to understanding cosmic symmetry in ways we have yet to imagine. If our universe is indeed embedded in a multidimensional space, then the symmetries governing it could involve intricate interplays between these unseen dimensions. Such interactions could give rise to phenomena in our three-dimensional reality that are currently beyond our comprehension. In addition to string theory, quantum gravity offers another promising pathway for exploration. This field strives to reconcile the seemingly incompatible principles of quantum mechanics and general relativity. As we probe the nature of spacetime at quantum scales, concepts like loop quantum gravity begin to emerge. These theories suggest that space and time might not be continuous, but instead quantized, potentially offering a revolutionary perspective on how symmetry operates at both cosmic and subatomic levels. Such revelations could reveal new, unknown forces that govern the very harmony of the universe, inviting us to explore the mysteries that still lurk in the cosmic shadows. Despite the progress made in theoretical physics, we are still confronted with significant limitations when it comes to unraveling the true nature of the universe. One of the most daunting challenges is the vastness of space itself. The universe is incomprehensibly large, and even the most powerful telescopes can only explore a fraction of it. To put it into perspective, the nearest galaxy to ours is over 2 million light-years away. This staggering distance presents a fundamental challenge in real-time observation, as by the time data is collected from distant celestial objects, they may have already changed or evolved, making it difficult to study them as they are in the present moment. Additionally, the universe presents an array of phenomena that exist beyond the range of human vision, from ultraviolet light to gamma rays. While we have developed specialized instruments capable of detecting these wavelengths, the technology is still not perfected enough to provide the clarity or reliability necessary for comprehensive analysis. As a result, we often find ourselves working with incomplete data, especially when studying complex cosmic events, such as supernovae or the formation of black holes. In many cases, researchers must make educated guesses based on partial information, which complicates our understanding of these awe-inspiring occurrences. The sheer complexity of the cosmos further deepens our challenges. One of the most confounding mysteries is dark matter and dark energy, two phenomena that make up approximately 95% of the universe's total energy density. These entities remain elusive because they do not interact with electromagnetic forces in ways we can easily measure. Our current cosmological models, while incredibly advanced, still cannot fully account for these unseen forces. This knowledge gap leaves a vast portion of the universe shrouded in mystery. Moreover, the challenge of data analysis is becoming increasingly pronounced. With the advent of modern telescopes and space missions, the amount of data being generated has reached unprecedented levels. This wealth of information often exceeds our capacity to process it and analyze it in meaningful ways. While artificial intelligence and machine learning show promise in helping manage these vast data sets, the technologies are still in their infancy. As we continue to refine our analytical techniques, we find ourselves at the crossroads of powerful data collection and the urgent need for effective interpretation, an ongoing challenge that will define the future of space exploration for years to come. Technological advancements have always been pivotal in expanding our understanding of the universe. The invention of the telescope in the 17th century, for example, allowed us to glimpse the moons of Jupiter, fundamentally changing our view of the cosmos. Today, massive ground-based and space-based observatories allow scientists to probe deeper into the universe than ever before. These technological strides not only enhance our ability to gather data, but also increase its accuracy, enabling us to observe celestial events and structures that were once beyond our reach. One particularly remarkable example of this technological evolution is the development of radio telescopes. These instruments allow us to capture radio waves emitted by distant celestial objects, providing an entirely new dimension to our understanding of the universe. Radio telescopes have unveiled phenomena such as pulsars, quasars, and the cosmic microwave background radiation, an echo of the Big Bang itself. When combined with optical and infrared technologies, these tools have given researchers a multifaceted view of the universe, enriching our comprehension of its structure and evolution. This ever-expanding arsenal of observational tools continues to open up new frontiers in our exploration of the cosmos. Advancements in computational technology are dramatically transforming our approach to the cosmos. With ever-increasing processing power, scientists are now able to run incredibly detailed simulations of cosmic events, things once only dreamt of. These simulations model complex scenarios, such as the violent collisions of black holes or the birth of galaxies. Insights from these digital environments are crucial as they reveal mysteries that observational data alone cannot unearth. Armed with the ability to analyze massive data sets, scientists can discern patterns and anomalies that help guide future research, expanding the boundaries of theoretical astrophysics. Moreover, the emergence of groundbreaking technologies such as gravitational wave detectors signals the dawn of a new era in observational astrophysics. These detectors, sensitive enough to capture the faintest ripples in the fabric of space-time, allow us to sense massive cosmic events like black hole mergers that otherwise go unnoticed. The ability to hear the universe in this way has opened up an entirely new dimension of exploration, granting us a more profound understanding of the cosmos. The innovations don't stop there. With every technological leap, humanity's ability to investigate deep, fundamental questions about the origin, makeup, and destiny of the universe expands. The tools of exploration are not only getting better, they're unlocking new layers of knowledge. These breakthroughs in turn push the boundaries of our understanding, reminding us that the universe is an ever-expanding frontier, constantly revealing new wonders, mysteries, and challenges that fuel our curiosity. However, despite the extraordinary progress we've made, there remain cosmic phenomena that still lie tantalizingly beyond our reach. Even with the most sophisticated instruments at our disposal, many of the universe's secrets remain elusive. This challenge is, in part, due to the sheer scale and complexity of the cosmos. When we look up at the night sky, we see stars and galaxies that seem so distant they appear almost insignificant. Yet many of these objects are billions of light years away, and the light we receive from them has been traveling for eons. As a result, the signals we try to capture are often faint, diluted, and distorted by the vast stretches of space they traverse. Moreover, the universe itself is a dynamic and ever-changing environment, filled with cosmic events that happen unpredictably and often on timescales too vast for us to fully monitor. Phenomena like supernovae or gamma-ray bursts can erupt suddenly, unleashing immense waves of energy and radiation. Because these events happen so quickly and can be located in parts of space that are inaccessible to our current observation methods, detecting and predicting them from Earth remains a monumental challenge. Even with our powerful instruments, there are still significant obstacles. Our technology, while impressive, is not without its limitations. Issues like resolution, sensitivity, and the overwhelming volume of data we must process make it increasingly difficult to extract meaningful conclusions. As if that weren't enough, the very nature of certain cosmic events makes them even harder to study. For example, black holes themselves don't emit light, so their presence is only detectable by their gravitational pull on nearby objects. This indirect method of observation makes it difficult to gather comprehensive data. Similarly, dark matter and dark energy, mysterious entities that together account for nearly 95% of the universe's mass and energy, do not interact with electromagnetic forces in the same way that ordinary matter does. Consequently, they remain nearly impossible to detect. As we continue to push the limits of our knowledge, it is clear that the future of astrophysical exploration lies in the development of new tools and techniques. Every advancement in observational technology holds the potential to unlock further secrets of the universe, yet the quest for understanding remains an ongoing journey. It serves as a constant reminder that there are still wonders out there waiting to be discovered. Looking to the future, the role of emerging technologies in astrophysics is becoming more and more apparent. Artificial intelligence, AI, for instance, will play an increasingly vital role. As telescopes and spacecraft gather more and more data, AI systems will be instrumental in analyzing and making sense of the sheer volume of information. AI could help scientists spot previously unnoticed patterns, identify new celestial phenomena, and even predict events that were once considered out of reach for human researchers. The ability of AI to sift through massive data sets with efficiency and precision will accelerate our understanding of the universe, transforming the speed and scope of our discoveries. Another promising development lies in the potential of space-based observatories equipped with cutting-edge instruments. Unlike Earth-based telescopes, which are affected by the planet's atmosphere and light pollution, space telescopes will have the freedom to observe distant stars, galaxies, and other celestial objects with unparalleled clarity. These instruments could revolutionize our ability to detect faint objects and measure cosmic events with incredible precision, allowing us to explore regions of the universe that are currently beyond our observational capabilities. In addition, advancements in gravitational wave detectors will give us a deeper look at some of the most violent and energetic events in the universe, such as black hole mergers and neutron star collisions. The data gleaned from these events will provide invaluable insights into the fundamental workings of the cosmos, enabling us to observe phenomena that were previously undetectable. Quantum technologies, too, are on the horizon, with the potential to revolutionize communication in space. Imagine a network of quantum satellites that can transmit information instantaneously across vast distances. Such systems would not only enhance global collaboration in astronomical research, but also drastically improve the precision and speed of scientific measurements. The precision offered by quantum technologies could transform how we study the universe, leading to faster discoveries and more accurate models of cosmic evolution. On a broader scale, the development of more advanced propulsion systems may change the way we think about space exploration. Concepts like ion drives, or even the theoretical idea of warp drives, could one day allow humanity to venture beyond our solar system and reach distant exoplanets within a human lifetime. Such breakthroughs would reshape our understanding of the potential for life beyond Earth and open up new frontiers for exploration. However, as humanity extends its reach into the cosmos, it faces a host of technological challenges that pose significant barriers to progress. Many of these challenges are not just technological, but are born from the inherent dangers and complexities of space itself. Space travel, for instance, requires the development of propulsion systems capable of reaching a significant fraction of the speed of light, which is no easy task. The closest star to our solar system, Proxima Centauri, lies over 4 light-years away, and current spacecraft would take decades, if not centuries, to reach it. Moreover, long-duration space missions present another set of hurdles. The effects of prolonged exposure to microgravity, such as muscle atrophy and bone density loss, are not fully understood, and these health risks must be addressed before extended missions can be undertaken. Similarly, the development of life support systems that can function autonomously, recycling air, water, and food supplies is essential for the success of deep space exploration. Finally, communication across the vast distances of space presents its own challenges. The further a spacecraft travels, the weaker its signals become. Effective communication with distant spacecraft could, in the future, become a monumental task, requiring advancements in signal processing and transmission technology. Despite these significant challenges, each obstacle presents an opportunity for unexpected discoveries. With each technological hurdle, there is the potential for new breakthroughs that could not only bring us closer to our cosmic goals, but also teach us more about the universe and our place within it. The journey itself holds the promise of new technologies and insights that will continue to push the boundaries of human knowledge. And as we venture deeper into space, we will likely find that the universe has more to reveal than we ever imagined.